Perfect. Oh, and yes, I would also add, of course, if you'd like to turn on your camera so that Ulrich and I are not just looking at each other, that's welcome as well. But of course, you don't have to do that either. Okay, so welcome to our tutorial on normalizing flows and invertible neural networks. So this is a half-day tutorial, which works out to about 4 hours. And it's going to be split roughly in half between Ulrich and myself. So I'm going to kick things off with an introduction to normalizing flows, as well as some example applications of normalizing flows in computer vision. So the intro is going to be about an hour. We'll probably have maybe some questions and some break time in there. And then I'll pick up with maybe another 30 minutes or so, 45 minutes or so of presenting a few recent works by myself and my team of some applications and extensions of traditional normalizing flow models. And then at around the 2 hour mark, we'll switch over and Ulrich will pick up talking about kind of the more general class of INNs, as well as some great flow work that's coming out of his group and some really interesting applications in computer vision and beyond. Okay. And so, as I said before, please feel free to ask questions or make comments in the chat. I will try to keep an eye on things as I'm going. If I miss things, don't hesitate to reiterate if you feel like I've missed your comment. Okay, so let's go ahead and get started. So we'll start off with an introduction to normalizing flows. And before we get there, I want to just give a really quick description of generative models, because this is a term that we hear a lot. We hear a lot about generative models, especially over the last 4 or 5 years. But what are generative models? Normalizing flows are a particular example of a generative model. And to motivate why I think they're a interesting and kind of increasingly important example of generative models, you kind of need to understand the context of generative models more broadly. And so a generative model is just a probability distribution over a random variable. Okay, so it's just a probability distribution. And we're going to try to learn that distribution typically from a set of observed data. And that distribution will have some probability density and presumably some parameters theta. And so once we have that generative model, we can, for instance, generate samples. We might be able to evaluate the density of new data points. We might try to compute expectations and various other properties of that distribution. And different choices of kind of the family of distributions that we look at and the way we do learning for the parameters given some data leads us to different classes or different forms of generative models, such as GANs, VAEs, and things like that. And so I'm just going to quickly run through a couple of examples of generative models to kind of set the stage of why normalizing flows are interesting and why they might be relevant to you and the applications that you're interested in. Okay, so the first and probably simplest generative model is mixture models. And so, and I have this in here in large part to point out the fact that generative models are not new. It's just kind of the word of the day for probabilistic models. This is something that people have been working on for a very long time. Gaussian mixture models is one example that has been extensively studied in statistics and machine learning and computer vision and lots of other places. It's been put to wide use. And is arguably kind of a classical example of this. And so it's trained typically using maximum likelihood, or actually some variational bound on maximum likelihood. So the EM algorithm for fitting mixture models is optimizing a variational bound on the likelihood. Sampling and evaluating the density is straightforward. But one of the challenges is that performance typically scales rather poorly with dimensionality. You can kind of fix this. So the images shown here on the right here, this was a paper from Yair Weiss's group a couple of years back when GANs were really blowing up, and it simply pointed out the fact that you could do pretty well with a Gaussian mixture model for generative modeling on a lot of these data sets if you were able to kind of handle the technical challenges of a Gaussian mixture model in a really high dimensional space. But they also scale relatively poorly in terms of added expressiveness, because in a mixture model, the only knob you have to really control expressiveness of your model is adding one more mode. And oftentimes the forms and the nature of complexity of distributions that we're interested in isn't about having one more disconnected mode. It's about having some complex correlation, and those get very data inefficient, for instance, to represent with a Gaussian mixture model. So another kind of classical but new again form of generative model are energy-based models. If you've been following the literature on generative models recently, you might be starting to see this term pop up again. These are models where you model effectively an unnormalized form of the density. And so this is a very familiar family of models in computer vision. Markov random fields is kind of the most famous example of an unnormalized energy-based model. But there's lots of others that have been used out there that have had success both classically and more recently. There's been some really interesting work kind of reviving them. The challenge with the energy-based models is that because all you have is an unnormalized density, training it can be quite difficult. And sampling from it as well can be quite complex and quite difficult, both of which typically require some form of Monte Carlo or MCMC. So if we go to what are now probably what people more typically think of whenever you use the word generative models, we get to things like GANs. And so generative adversarial networks, introduced by Goodfellow and others in 2014. Training is done through an adversarial process, which is a bit finicky, a bit tricky to get to work. But that training, roughly speaking, kind of minimizes a divergence between the generated samples, the distribution of generated samples in your data distribution. And sampling is very straightforward for GANs. That's it's right in the name in some sense. But evaluating the density is at least usefully evaluating the density is generally not possible. It requires a fair amount of work to do that. And so that somewhat limits the applicability of GANs. And the other generative model that's pretty common that people often think of when you say generative modeling today is variational autoencoders. So you've probably seen these. They're a probabilistic latent variable model. And they they have been actually very successful in learning low dimensional representations. They are trained by a bound on the marginal likelihood, and sampling is relatively straightforward, but density evaluation is actually not. You can only actually evaluate basically a stochastic approximation of the density. I see some questions here in chat. And somebody's asking about stochastic diffusion models, and that is an excellent question. Those are a very new class of models that have been really interesting to see emerge within basically the last year. I would probably argue that they are a separate class of models as well. They work a fair bit differently than kind of any of the other ones that we've talked about so far. Okay, so we have these kind of family of tools. We have things like Gaussian mixture models, which are relatively easy to work with, simple to understand, simple to sample from, but not particularly expressive in the ways that we want. We have things like GANs, which get us, very impressive results, but are hard to work with sometimes in terms of training, and they don't allow us to evaluate density, which is often useful in some applications. We have VAEs, which is a bit better. The results are not typically quite as good for VAEs, although that's changing, at least in terms of perceptual quality of generated imagery. But training is a bit more straightforward. Density evaluation is possible, at least approximately. And so normalizing flows is going to kind of fit in here in an attempt to kind of check all those positive boxes in one class of models. Okay. And so normalizing flows are a form of generative model that are built on invertible transformations. And so kind of generally speaking, what can we say about them at a really high level? They're generally efficient to sample from. They're generally efficient to evaluate the exact density. So both of those things are possible and for the most part efficiently doable. They are highly expressive. We have the ability to kind of tune a variety of knobs, in fact, to kind of increase complexity of the distribution relatively straightforwardly. And They also give us a potentially useful latent representation. We'll talk about that a bit more later. And for the most part, they're straightforward to train. And so they kind of check all the boxes. They haven't seen as much attention as things like GANs and VAEs, and so the perceptual quality of the generated imagery is still, I would say, is catching up, but actually catching up very, very quickly. So question here about VAEs and optimizing a bound on the likelihood. And pointing out the NVAE paper. So indeed, NVAE is an excellent paper. It is state of the art, I would say, in terms of image quality for VAEs. There's an interesting question here, which is a much longer tangent, which I'm happy to come back to later. Whether or not image quality has to do with the inherent structure of the model or the objective function that you use to train it with. And things have kind of gone back and forth. NVAE is kind of a nice data point that proves that likelihood-based training or even variational bounds on likelihood-based training are not an inherent limiter to image quality. Yeah. Okay. So this is what we're kind of hoping for with normalizing flows. Let me walk through just a really quick history of them and kind of where they came from. The idea actually goes back to around 2010 this is a paper that was eventually published in an applied math journal by Tabak and Turner. That this is where, at least as far as I'm aware, the first instance of the term normalizing flow. And it was just looking at defining kind of a more flexible family of density functions and probability distributions. A couple of years later, there was this paper by Ryan Adams and his group from Harvard, and looking at using these models for density estimation. And this was interestingly kind of a paper that was posted on arXiv and never really, I don't think it really got noticed that much at the time, but it was fundamentally doing a lot. It had a lot of the core ideas of what we're about to do. And then things started taking off about a year later with NICE, which was looking at using these invertible models to do a form of nonlinear independent component analysis, a nonlinear ICA, by Lawrence Din, I believe at the start of his PhD studies. And then next year, the year after, we saw this work looking at using normalizing flows and variational inference, where they weren't really looking at using these normalizing flows directly as a generative model. They were viewing them as a way to construct more complex prior distributions for and approximate posteriors for VAEs. Okay, and then the kind of steady trend of work in the space continued until we got to 2016. When the real MVP paper came out. So this was again Lawrence Din and his work. And this was kind of the first case where we started to see, you know, plausible imagery being generated from normalizing flow models. Now, this is 2016, you have to bear that in mind. And so these images now look kind of bad as far as generative models are concerned, you know, but they're actually kind of in the same ballpark as a lot of what was being generated at that time, in that, you know, you squint at it, they look natural, but of course, if you look closely, they have some fairly obvious artifacts. Now, the interesting thing about this paper, and you'll hear real MVP as a model referenced a lot, and it's because basically a lot of the core ideas that are now still widely used in normalizing flows were introduced in this paper. But the resulting images weren't hugely impressive. But it was definitely an interesting class of models. And about 2 years later, Deirdre Kingma at OpenAI introduced the GLOW paper. And this, in my mind, you know, so real MVP in 2016 was kind of a landmark in normalizing flows in terms of introducing the concepts. GLOW, I think, arguably, GLOW didn't introduce a lot of new methodology to normalizing flows. It had some novelty, but it wasn't huge. But a lot of what it did was it took the ideas of real MVP and just trained it bigger and harder, in a sense. And it's the paper that I think got everybody's attention because it was able to produce these sorts of really, really impressive high resolution imagery using just these, flow-based models that have these properties of efficient sampling, efficient density estimation, and so forth. Okay. And it also had the benefit of a reasonably useful latent representation that kind of just came naturally with the model that would allow you to do things like naturally morph between people's faces, where, unlike with GANs, this was something that we'd seen people doing already with GANs, kind of interpolating in the latent space. But that was always interpolation of images that were generated by the GAN, as opposed to interpolation of existing real images. And so what we see here is morphing back and forth between famous pictures of famous people and one of the authors, right? And that's possible because of the nature of the invertible representations in normalizing flows. Okay, so that's prelude. So let's get to some of the meat of this. So what are normalizing flows? At the core of it, if you wanted to say it most succinctly, most concisely, most directly, I would argue that normalizing flows are, in some sense, a glorified application of a basic result that we see in a probability course, which is the change of variables. Okay, so this is a standard result in probability that relates two random variables, x, through some function f to a random variable z, where f is going to be some invertible differentiable function, and it relates the density between these two things, right? So in other words, it gives you the answer to the question of, if I take a random variable x, I run it through some invertible transformation f, how does the density of that original random variable x and the new random variable z, how do those two things relate? Okay. And so it turns out that they relate kind of the way you would expect. You just run it through your invertible transformation, and the densities at those 2 points are equal, except that you have this added volume correction term. Okay. And this volume correction term, it basically, you have to have this here in some sense because we need probability densities to integrate to 1. That's where this comes from. Okay. And in fact, you can derive the change of variables formula pretty straightforwardly from the constraint that the densities have to integrate to 1 with an application of the change of variables for integration formula from calculus. Okay. And so in terms of pictures, we can think about it this way. We start off with our distribution, some complex distribution over x, maybe. It's this kind of peaky bimodal thing. We take that random variable x, we run it through an invertible transformation. In this case, I've selected the cube root of x, which you can check for yourself is indeed a invertible function. Its inverse is, of course, just x cubed. And if we take that distribution, we can use this formula to work out what the density is of that transformed variable. And it turns out it's now just a nice unimodal distribution. Okay. And so, I mean, you can kind of see the precursor of the name normalizing flows, because these invertible transformations are in a sense changing the distribution from some complex form into a normal distribution and therefore normalizing it. Okay. And so taking this together, what this means is we can represent some given complex distribution P of x in terms of, let's say, a arbitrary simple distribution that we select, the distribution over z, and the invertible transformation f. Okay, so maybe we have our big complex distribution of images of trees, and we have our distribution over z, which is going to be Gaussian noise, and there's some function f which will transform this distribution over x into a distribution over z, right? Into this Gaussian distribution, right? Transform these images of trees effectively into white noise. Okay, and I should say, just kind of as a side note, there's some nice theory and statistics and probability that basically tell us, if f can be arbitrarily complicated, we're pretty much free to choose z to be whatever we want. There's a few little asterisks and caveats to that for the mathematical pendants out there, but But that's mostly true, all right? So we're free to choose this distribution over Z to be whatever we want. And so we're typically just going to make it Gaussian, okay? And so a normalizing flow basically then has these two pieces, right? It has this base distribution or this base measure or latent distribution. It goes under a bunch of different names, typically selected as a multivariate Gaussian with unit variance. And then we have the flow, which is this function f that has to be invertible and differentiable in order for the multivariate change of variables formula to apply, okay? And so if we have those pieces, what can we do with this? Well, density evaluation is actually trivial, right? It's exactly our change of variables formula here, right? So if we have some new x and we want to evaluate the density of that new x, well, we take it, we run it through our function f, we transform it into Gaussian noise, and now we can evaluate the density of that point under the Gaussian distribution under that base measure. And if we take that and we multiply it by that volume correction term, which we'll talk about more later, then we get the density of our kind of complex distribution x, okay? The other thing we can do that we've talked about with kind of other models is sampling. And sampling is kind of nice because basically we can draw to sample from our distribution over x. Now, what we need to be able to do is sample from the distribution over z and compute the inverse and basically map the other direction, right? So we take a sample and we run it through f inverse, and we end up getting a sample from the more complex distribution, okay? And so we take all these pieces together. Now we can ask things like, well, how do we train this? Okay, so if we've fixed Z to be a Gaussian distribution, and we have some parametric form of our function f, then how do we learn the parameters of that transformation f? Okay, and so the kind of first most obvious answer is through maximum likelihood. Okay, so we can just write out the likelihood of a bunch of data points xi, and we end up with this form here where we have a sum over, let's see if there we are. So we have a sum, and we have the log density of our base measure or our Gaussian distribution here of our x's under the transformation. And then we have this added log determinant term here, which is basically the log of the volume correction term that gets included. Okay, and so we can just take this, we can write this out, we can differentiate it and do training with it, right? Using standard stochastic gradient descent and all the other tools and tricks from deep learning that we know. But of course, what I haven't told you anything about yet is what are these flows themselves? How do we actually construct them? Okay, so that's what we're going to cover next year. How do we get these invertible differentiable parametric functions that will allow us to transform arbitrarily complex distributions into nice, simple Gaussian distributions? Okay, so well, let's just be concrete. What is a flow exactly? So a flow is a parametric function that has to be invertible. It has to be differentiable. These are the kind of two basic properties required from the change of variables formula. And then there's kind of a third, I guess, more practical constraint that I put in there myself conceptually, is that we have to be able to efficiently compute both the inverse and the Jacobian determinant. Okay, and basically, those first, you can have an invertible function whose, we can mathematically guarantee it's invertible, but its inverse might be very complex to compute. And similarly, we have a function that we can differentiate and get a Jacobian and take the determinant of it, but that might be a very expensive operation to do. And so we want these flows to also have kind of efficiently computable inverses and Jacobian determinants. So Bradley's asking here, yeah, exactly. Yes, that's right. We can use this to basically train a function that maps a distribution of images into a distribution of latent vectors, which has arguably any PDF you want. Again, there's a few little theoretical intricacies there that I'm hand waving over, but basically any distribution you want. Okay. All right. And so these are typically called a flow layer. Sometimes people use the term bijection. My mathematician friends object to using the term bijection because technically bijective transformations don't have to be differentiable, whereas we do need differentiability for the flow. But you'll see this terminology used, and I will sometimes jump back and forth between these different variations myself. And so designing and constructing and kind of understanding the property of these flows is really kind of the core technical challenge with normalizing flows. All right. And so how do we solve this, and how do we have the ability to kind of build up arbitrarily complex transformations, which is arguably what we really need? Well, we're going to kind of take a page out of or you can argue inspiration out of deep learning, where, you know, arguably deep learning is about constructing arbitrarily complex nonlinear functions generally. And we do that by kind of constructing successively deeper, kind of more complex transformations by kind of layering or composing simple nonlinear transformations one after the other. Okay. I see a couple of questions here in the chat. So Rohit asks, are invertibility and bijection the same thing? So basically, yes. But note that a flow also has to be differentiable. So a bijection doesn't technically have to be differentiable, right? So we need that differentiability property as well, which is why I said some more mathematically inclined people object to calling these flows bijections, or just simply bijections. Okay. And then Kaushik is asking how the invertibility constraint is practically established. We'll see that basically we're going to prove for every flow that we construct that the transformation is invertible, and we'll do that basically by explicitly giving the inverse. Okay, and absolutely, Ulrich, the term diffeomorphism is kind of the technically one other term which is a bit more precise for the mathematically inclined, or differentiable bijection as well. Exactly. Okay. Great. Yeah. And again, please keep the questions coming. I'm happy to have these. It makes this way more fun, and it means people are actually awake, which is good. Okay. So coming back to constructing arbitrarily complex transformations, invertible transformations, arbitrarily complex flows, you know, we can use this property of invertible differentiable functions or flows, that they're closed under composition. Okay. And what does that mean? Well, that means that if I have a bunch of flows, so a bunch of invertible differentiable functions, a bunch of diffeomorphisms, F1 up to Fk, and I compose them all together, then the resulting function F, that's just the composition of all of them, is also an invertible differentiable function. And so just like in deep learning, where we construct arbitrarily complex nonlinear functions, we can construct complex flows by composing these simpler kind of building block flows. Okay. And so just kind of to illustrate that visually, you know, you can think of starting off with our complex distribution over here. And instead of trying to transform that thing into a Gaussian in just one shot, maybe we have one simple transformation which just does a little bit to the distribution. Okay, so it scales down, you know, these modes, kind of smooths things out a little bit. That's F1. And now we have F2, which kind of continues this process, smoothing things out a little bit more. F3. And F4, until eventually we gradually transform this through a succession of relatively simple transformations. And now we can just compose that all together conceptually into just one single invertible differentiable function. And now the inverse is basically just the composition of each one of these individual simple transformations to get us back from this simple Gaussian distribution into this more complex kind of multimodal thing on the left here, right? And again, the inverse of the entire transformation is just the composition of all the individual inverses. Danny R is asking if the distribution over Z can be a discrete distribution. So I said there were some technical little details that that I was hand waving over, and that is one of them. Basically the technical detail is that the topology of your data distribution and the topology of your base distribution has to effectively be the same. Okay, so if you're fitting a continuous distribution, you can't easily have a discrete base distribution, at least within kind of the basic framework that we're discussing here. There has been a little bit of work extending normalizing flows to discrete distributions in a number of different ways, including looking at invertible transformations on discrete spaces. We're not going to be talking about that today, so it's a bit more complex, but there has been some work in that direction. Okay, so we have these composition of flows, and now what are the properties that we need to satisfy? What are the things that we need to be able to do for a flow to be practically useful? If all of these kind of subflows, as you will, right, these kind of more basic flows are invertible and differentiable, we know that the entire composition is going to be invertible and differentiable. We just kind of illustrated that here, but we also need things like the determinant. And so we can use some basic properties of determinants and some basic properties of composition of functions to show that the determinant of the entire transformation is just the product of the determinants of all the individual transformations, right? So, so that's kind of nice. So if each one of these simple flows has a simple determinant, then the determinant of the entire thing is also going to be this relatively simple product, okay? Similarly, the likelihood, again, you can take this definition of the determinant, and what we get is, now we have this additional summation in our likelihood term, which is now a sum of each term, which includes the log determinant of each layer of the transformation. Okay. Yes, Piyush is asking if the latent distribution is going to be a mixture of Gaussians. Absolutely. And in fact, there's kind of theoretically, you can choose your latent distribution to be anything. And if your class of invertible transformations is sufficiently expressive, in theory, you can learn it to transform to whatever base distribution you want. But kind of a big, open, interesting area in normalizing flows from my perspective is what's the practical influence of this choice of base distribution? Because it turns out it does actually have some impact practically when you restrict yourselves to certain classes of flows, okay? All right, so we know now that we can take simple flows and compose them together to create more complex ones, all right? But what are those simple flows? I still haven't told you what those are, okay? And so if we just stop and sit back and think for a second and ask ourselves, what if I had to design an invertible function? What is a particular invertible function that I can build? What's a simple invertible function I can build? And one of them would be just a simple linear transformation, okay? So a linear transformation can be a flow if the matrix that defines it is itself invertible. Okay, so our flow function f of x can just be ax plus b, right? That is a valid flow so long as the matrix A is invertible. Its inverse here is given by this expression, excuse me. And the determinant of the transformation is just the determinant of the matrix A. Now, of course, there's some problems with this. The biggest one, to be honest, is that a linear flow in and of itself is not terribly expressive. Okay, and that's basically just because linear functions are closed under composition. So if I stack a bunch of linear functions on top of each other, I'm still left with just one linear function. And we know that we need to be able to do nonlinear transformations in order to make these flows do anything particularly interesting. Okay. The other challenge, though, is that the determinant or inverse computation for the inverse pass could be order d cubed in the dimensionality, right? So cubic in the dimensionality of the space of your distribution. And it turns out linear flows are going to be kind of important for other things later, where we're going to use them in a particular way. And so there's been a fair bit of work looking at different simplifying assumptions you can make on the structure of these linear transformations that basically reduce the costs of the inverse and determinant calculation by either enforcing some particular structure on the matrix itself. Okay. And so, there's a couple of papers here that I'm citing here that for instance, implement convolution in various ways, that do, propose factorizing the matrix and representing it in terms of its factorized forms, which is this LU factorization and so on. Okay, so let me just take a quick look at, before I go into this next section here for questions. So Rob's asking, terminology sounds a lot like manifolds. Yes, there is definitely a much more general, mathematically sophisticated kind of, I guess, generalization of normalizing flows that defines them on kind of more general Riemannian manifolds. That's well beyond what we're going to cover in this tutorial. There's a couple of papers that I have out that you can take a look at. It's also related to things like optimal transport and a lot of other really interesting areas as well. And there has been a work, including a recent paper from myself and some collaborators at Yale, looking at normalizing flows in different ways to distributions on manifolds. Okay. Chen is asking about the Fourier transformation as the function f. So absolutely, the Fourier transform absolutely can be used as a function f. In part, the Fourier transform is just another linear transformation, right? It's just a very special linear transformation that has a lot of nice properties. And in fact, Fourier transform has the particularly nice property that its inverse is efficiently computable because it has that special structure. And in fact, the determinant of the Fourier transform is just 1 because it's an orthonormal transformation, right? Okay. So now we have, we've talked about composition of flows, so we can take flows and build them up to more complex things. I've shown you a really basic flow, which is a linear transformation. But if all we did was compose linear transformations, as I said, we wouldn't get anywhere. We'd still be within the family of kind of linear transformations. And so we need something nonlinear. And that's where coupling flows come in. Okay. And so this was, if you recall briefly at the start, I mentioned real MVP and the work by Laurent Din. These coupling flows is really kind of the core component that came out of those papers, the nice and real MVP papers, that has really kind of laid the groundwork for a lot of the work that came later. It's not everything is coupling flows, but most, many popular architectures and papers that are coming out are using these coupling flow structures. Okay, so what is a coupling flow? So I'm going to describe this visually, and then I'll write out the math because I think the visualization is clearer than the math, which is not something I say very often personally. Okay, so for a coupling flow, we have some input x. Okay, and what we're going to do is we're going to take that input and we're going to split it into two pieces. Okay, we'll call them XA and XB. Okay, so these two halves of our space. How we exactly split it, don't worry about that. We'll talk about that a little bit later. And XA, we're going to handle each of these pieces differently. So first off, we're going to take XA and we're going to go ahead and just take a piece of it and set it to the side. And we're not going to change it at all. Okay, it's not going to be modified. Okay. But what we're going to do is we're going to take XA as well, and we're going to run it through something called a coupling network, which is going to be a function theta. And it's going to give us a set of parameters. And those parameters are going to define a coupling transformation, which is going to be another type of flow. Okay. It's going to be a simple flow. And in fact, it could potentially be a linear flow. Okay. And let's call this coupling transformation f hat. Okay, so now we have this, we've applied this coupling transform to XB. Okay, so this is going to be an invertible differentiable transformation whose parameters are some function of XA. Okay, so now we have in our vector representation XA and then the transformed version of XB. Okay, and we're going to stick them back together, and this is going to be the kind of forward pass of our coupling flow, right? So we can write the whole thing down mathematically to look something like this. F of x is just going to be equal to XA in the top half, and then F hat of XB in the bottom half. Okay. So is this invertible? Well, because we have not changed XA at all, we've not manipulated that at all in this particular step, then this block is invertible, right? And how do we do that? Well, we have our inverse. We start off with Z now. Okay, we'll start on the other direction. We're going backwards. okay? And we're going to again split it into ZA, but remember that that first component of Z is just XA, unchanged, and so its inverse is just to take it and pass it straight through. But that means that we still have that original XA that was passed through the coupling network, and we can do that again to get our set of parameters theta, and we can use that to now get the inverse coupling transform that we used. That will that we can apply to ZB here to get back our original XB, and now we can concatenate them back together. Okay, so this is the inverse of these coupling flows. Okay, questions here. So here's so Param's asking if the output of the coupling network has to be checked for invertibility. Okay, so here's the cool thing. We'll get to this in a minute. But it turns out we don't actually care what the coupling network does. Okay, that thing that predicts the set of parameters, it can be absolutely anything. I'll explain why and how that can be the case in a minute. But theta can be anything you want. Okay, and Moritz is asking about the splits. So no, the splits cannot be overlapping. The splits have to be a disjoint subset. It has to be a disjoint split. Okay, so XA and XB cannot overlap. Okay. Okay, so we have these coupling flows, but if you haven't seen these before, it might look a little strange. It might look a little artificial. And so why is this a good thing to do? Why is this a valuable thing to do? And so to understand why that's the case, let's take a look at the Jacobian of the transformation that we have. Okay, so the Jacobian of F here is this matrix here. I'm going to go through this briefly here. So in the top left corner, we have the derivative of ZA with respect to XA, right? And so remember, we're not changing XA at all. So this is just the identity, okay? And now we have the derivative of ZA with respect to XB, okay? And this is 0 because, again, we didn't change XA in any way that depends on XB. We didn't change XA at all, okay? Now we go down to the next row. Let's take a look at this entry. So this is the Jacobian of our coupling transformation, okay? That kind of smaller flow that's only applied to XB, okay? Because this is the derivative of ZB with respect to XB. Okay, so this is our Jacobian of our kind of simpler of our coupling transformation. And then this thing here is the derivative of the coupling transformation with respect to XA, which potentially involves differentiating through theta, okay? But the thing is, we don't care about the Jacobian of the transformation. Not really. What we care about is the determinant of the Jacobian of the transformation, okay? And a coupling flow is structured in this particular way in order to have this very specific block triangular structure, okay? And so the determinant of a block triangular matrix is just the product of the determinants of the diagonal blocks. Okay, and so the determinant of this first block here, the identity matrix, is just 1. And the determinant of this is just, well, whatever the determinant of that thing is. Okay, so that means that the determinant of this whole coupling transformation boils down completely to just the determinant of this coupling transform. Okay. And so what that means for us practically is what I was alluding to earlier, that theta here, this function of XA, can be arbitrarily complex. And it can allow us to express really complex, very nonlinear transformations, or nonlinear relationships between the dimensions in XA and the dimensions in XB, okay? There's a little bit of a caveat here, which is that it's pretty important to change up the way that we do the splits to ensure full expressiveness, because obviously, if we're only manipulating half of the dimensions and leaving the other half completely unchanged, remember, XA is never changed. So if that's always the same set of dimensions every single time, then those are going to be unchanged. But how do we actually do that? Well, one simple way is to just throw in a random permutation or a linear transformation. Okay, so real MVP used effectively random permutations of the dimensions, right? Where we take our X and we just kind of shuffle the entries around. The Glow paper from OpenAI used a linear transformation. This is arguably their 1-by-1 convolution. I don't love that terminology, but it is what they used. But the point is that you're taking your dimensions X before, kind of repeatedly throughout the transformation and kind of shuffling them and mixing them together, right? And so now we can go ahead and split after they've been shuffled and we go through and do the standard coupling transformation again, and that gets us these manipulations, okay? So these are coupling flows. Now, what do people actually use for the coupling transformations themselves? Well, basically, people use things that look a lot like, people basically use the linear flows that we mentioned earlier. Okay, so I told you there's a reason I was going to talk about linear transformations, even though they are closed under composition, and that's because we can use simple linear flows as our coupling transformation in these coupling layers. Okay, and in fact, the original nice paper that was doing kind of nonlinear ICA by Laurent Din just used a simple additive transformation, so there's not even a scaling component to it. Real NVP introduced the ability to kind of rescale dimensions. So the parameters are now both the scale and the translation, the T here. And remember, S and T, for instance, in the affine case here, are going to be parameters of XA, so parameters of that other half of the transformation, right? And then there's many other variations of this. People have looked at using restricted forms of multi-layer perceptrons. People have looked at using splines and a lot of other kind of variations on transformations. And the key just is that this thing has to be invertible, right? And it has to be invertible. We have to be able to compute the transformation. And so the most common form of coupling transform, though, is probably this affine transformation. And so if you go back to our original diagram here that I'd sketched out of what a coupling flow looks like, all we're going to do is replace that general coupling transform with an affine transformation, and that gets us a transformation that looks something like this. So if we put it all together and kind of substitute things in, now we have these functions S of XA and T of XA, which produce the scaling factors and the translations that get applied to XB. Okay. Let me just take a quick look at questions here. If I fix the splitting for a single coupling flow and then have multiple coupling flows, each of them operating on a different split. Yeah, so Piyush here, basically, you can view this either as choosing to do different splits, randomly selecting your splits between XA and XB in each step, or you can always just take the top half and the bottom half as XA and XB respectively, and then randomly permute or transform in between, and you get effectively the same thing. Okay, let's see. Oh, and one thing somebody asked earlier about if the determinant becomes 0. This is something that is, I'll just mention here briefly as an aside. You do have to be a little bit careful sometimes about the way, for instance, these scale networks are implemented, because so this whole thing is invertible so long as S here, for instance, is not 0. And as S gets closer and closer to 0, the determinant gets close to 0, and you may run into numerical stability issues. And so there's a variety of kind of, I guess I'll call them hacks, to be direct about it, that people use to try to keep S here away from 0. Okay. So this is kind of the general concept of coupling flows. I want to mention some work by Ulrich and his group, which I think is really nice, because there's some nice theory from the probability side of things that basically says if you had a transformation with a dense lower triangular Jacobian, you can construct any transformation between any two distributions. Okay. And one of the problems with coupling flows is that it is not a dense lower triangular Jacobian, right? In fact, this is what the Jacobian matrix looks like. We have these entries on the diagonal for an affine coupling transformation, for instance. So we might have these might be the identity, and then these here on the diagonal of the Jacobian are just going to be the entries of that scale vector. And then maybe we have some dense stuff happening here that can kind of build really complex relationships between these two halves of parameters. But there's kind of what's happening here. So what about the correlations between these two, between dimensions within XA or dimensions within XB? And it turns out that you can kind of extend this idea of coupling flows to apply them recursively, so that basically when you apply the transformation down here, you again do another split, okay? And I'm not going to go into the details here. You can check out the AAAI paper, or I don't know, Ulrich, if you're planning to talk about this in more detail later. But the net result is that you go from having a Jacobian matrix that looks like this, where you have kind of these big holes, to something that is in general dense. Okay. Okay. So let me see your questions here. So Shubham is asking examples of flow transformations and natural processes. It's an excellent question, and I'm going to refer you to the second half of my talk in about a half an hour, 45 minutes or so, where I talk about noise flow. And I actually, one of the things that I really like about normalizing flows is actually the fact that the transformations you're building are in fact you are directly describing the process by which kind of independent, simple noise gets transformed into whatever it is you're modeling. And so, for instance, in the noise flow work, which I'll talk about more later, we're modeling camera noise. And we know a lot about how something like simple Gaussian noise should get transformed into real noise in a real camera. Okay. And so we construct certain types of flows that are inspired by that. So Nikos is asking about Yazan's asking about the dimensionality. So short answer to your question is yes, the dimensionality has to stay the same, but I'm going to get to that in a minute. And we'll talk a bit more about it. Okay. Okay. So, and then Pascal's asking about invertibility and learning on manifolds. So, so yes, the dimensionality has to remain the same for these transformations. So that can be a problem practically. I'll talk about some solutions to that in a couple of slides. We don't, there's density estimation, and then there's a sometimes closely related problem of manifold learning. And it's important to recognize that normalizing flows is more kind of strictly targeted at density estimation than it is at manifold learning. And so there is some work that tries to bridge that gap that I'm not going to go into, but yeah. So Param, you are actually very nicely setting up my next set of slides here. Coupling layers are, you can either view a coupling layer as a basic form of an autoregressive operation, or you can view autoregressive models as a form of normalizing flow. So take your pick. You can go one way or the other, okay? So I won't go into autoregressive models here in great detail, but basically they work by kind of factorizing these distributions into a sequence of univariate conditional distributions, okay? So the probability of xi given all the previous x's, okay? That's the basic idea. And they often are implemented using something called the reparameterization trick, which we've seen before. And so if we have Gaussian marginals, if we assume that the distribution of xi given all the previous x's is just a Gaussian distribution where the mean and the variance of that Gaussian distribution might be some arbitrarily complex neural network function, we can use the reparameterization trick to kind of express these Gaussian autoregressive models as flows, as just a simple element-wise linear transformation, or in fact, you can think of it as a coupling transform where xb is just a single dimension and xa includes, d-1 dimensions, okay? And this is kind of a nice conceptual concept because it tells us that autoregressive models and normalizing flows are not fundamentally different. If we look at autoregressive models as a type of flow, though, they have some very particular characteristics, okay? And so if we write out the transformation for an affine autoregressive flow, we get something that looks a bit like this, and we have its inverse, right? So we can easily do that inverse, and the determinant is just going to be the product of all of these sigmas, okay? But there's a bit of a challenge here, which is the sampling for autoregressive models is very slow, okay? And so this is generally well known in autoregressive models. We can train them relatively efficiently, but if you want to sample from them, you have to sample one individual pixel at a time, because the distribution of pixel 2 is dependent on the value of pixel 1. The distribution of pixel 7 is dependent on, pixels 1 through 6. And so we really have to generate these one at a time, okay? But the density evaluation, in other words, going the other direction from a flow perspective, can actually be done relatively efficiently in parallel, okay? And one of the reasons why I wanted to talk about these autoregressive models in this context is that something interesting about these flows, we think of them, the term bijection, invertible functions, you can kind of think of orienting them in either direction, okay? And so this was actually pointed out by I believe Ian Murray and Deirdre Kingma in a paper where they said, well, look, what if we just change the direction of the flow? Okay, so the thing that we called the forward direction, let's call that the inverse, and the thing that we called the inverse, let's call that the forward direction, okay? And so now we can go ahead and do that, and we get equations that look like this. These look a lot like the equations that I had on the previous slide, okay? And the determinant is basically the same, okay? So it's again just a product of those things. There's an 1 over that shows up here because we've flipped the direction around, okay? But now what we've done is, in the original autoregressive models, density evaluation was relatively efficient and could be done in parallel, but sampling was slow. Now we have a model where sampling can be fast. Density evaluation, however, might be slow, okay? And these are inverse autoregressive flows, okay? Any questions on this before we go? We're going to talk a little bit about dimensionality. Okay, so I think there's not too much in the chat here that hasn't already been answered. Asking about slides and video, yeah, we'll put the recording up afterwards. Okay. All right. So we've already had a couple of questions. Some of you have already noticed this, that invertibility of these transformations in essence requires us to preserve dimensionality. Okay. And so this can conceptually be very expensive in high dimensions. Okay. But there's a relatively simple trick to getting around this, at least from a practical perspective, which is we can just stop using subsets of dimensions. Okay. In other words, if we have our input, we start applying some invertible transformations, and now we just take half of them and we stop transforming them at all. All right. Because the identity transform is indeed just an invertible transformation. Okay. And practically speaking, this acts like dropping dimensions. Okay. If you think about it in terms of like constructing your computational graph in PyTorch or TensorFlow, it means the graph stops getting more complex for half of your state space. Okay. And this is the idea behind multi-scale normalizing flows, which was a kind of an architectural insight in the real MVP paper that is now pretty widespread in architectures. And just to give a sense of how this works, let's walk through it. So imagine we start off with our input X here, and maybe our first flow F1 here transforms everything. Okay, so all the dimensions get changed. But now what we're going to do is we're going to split it in half, and we're going to take the top half of it, and we're not going to touch it. We're done transforming that. That's going to go ahead and go straight into Z. Okay. And now F2 is only going to operate on the bottom half of this vector, the red and the green components of this vector. Okay. And then we can do the same thing again. We take the red components here, we split them off. We say, okay, now that's done. We've not changed those. That's going to go straight into Z. And now we have F3, which only manipulates these last pieces. And you can kind of keep going like this. Okay. And so now we construct Z as kind of all these different pieces, but note that we've only applied one flow at the kind of full dimensionality of the distribution, or the full dimensionality of the data. Okay. This is kind of a form of multi-scale representation or multi-scale modeling. It's not exactly multi-scale. I'll talk a little bit more about that later when I talk about wavelet flow, in the sense that we often think about multi-scale models or scale representations in computer vision, because it's not it doesn't map directly onto, let's say, resolution or image scale. Okay, even though it feels like it kind of should, it maps a bit more onto kind of scale of complexity of the distribution. Okay, because those components that get, the top components here, these only get a relatively small amount of transformation, and therefore their influence on the final distribution is in some sense kind of closer to Gaussian, if you will. Okay, it's a little bit of hand wavy, but just trying to give a bit of intuition. Okay, mathematically, these flows, they're invertible because we haven't lost anything. You can kind of think of them just as like a special form of a coupling flow where there is no coupling network. Okay, theta is just constant; it doesn't depend on XA. Okay. And there is just the important thing that we do need to kind of keep track of those dropped dimensions in order to preserve invertibility. And so when we, for instance, evaluate the base measure, when we evaluate P of Z, we have to have included all of those dimensions that we were using, even if we stopped transforming them, in order to satisfy the invertibility condition. Okay. Now, of course, this does raise a bit of a question for us, particularly in computer vision, where we're modeling images, which kind of has a certain spatial structure, and which is how do we actually split the dimensions for the images? The natural way to do this is to split by channel. Okay, so we start off with our X, which is some width, height, and maybe 3 channels for RGB. And we might want to split things up along those channels. And that would be kind of a natural way to do this, both in terms of the way that we do splits, for instance, for coupling flows, as well as the way that we implement these multi-scale transformations. But the problem is we only have 3 channels, right? We can only do so many splits. And so we have to do something else to effectively give us other reasonable ways to split this. And so there's what's sometimes referred to as a squeeze operation, where we take the spatial arrangement of pixels and we kind of group them together and stack them on top of each other in order to get a smaller spatial dimension, but with a larger number of channels, right? So for instance, maybe we start off with an n by n by c image, we apply the squeeze operation and we stack everything together, and now we end up with an n/2 sized image, but with 4 times c channels. Okay, and now we can, and so typically now these multi-scale architectures are going to involve multiple rounds of squeezing the spatial dimensions down to create more channels, followed by these splitting operations, either for the multi-scale construction or for the coupling layers. Okay. So Kaushik is asking actually what I think is a really interesting question, because I'm going to turn what he thinks is a problem into a feature. So Kaushik is asking, is there a way to avoid trivial solutions where the transformations are identity and the Jacobian is the identity? And I'm actually going to argue that that's actually what you want to do to initialize these models. Okay. It's not a trivial solution in the sense that once you start doing learning, it will diverge away from that, because typically that's not a particularly good approximation of your distribution, right? Because if all of your transformations are identity transforms, then that basically says you're starting off where your model in the data distribution, your model of the data is just an IID multivariate Gaussian, okay? But it turns out that the fact that we can construct all these transforms to be close to identity transformations, and we can construct that initial distribution to be close to Gaussian, is actually kind of helpful, because it knows that, because we can construct it in a way that, for instance, the mean and variance of our distributions already match just from day one. And that means we're already in the realm of kind of reasonable or plausible distributions, right? Okay. Right. So a few last things. So far, we've been talking about what are called discrete time normalizing flows, where we take, some complex distribution and we map it through a discrete set of steps. So maybe we map it through 4 different, invertible transformations in order to map our complex distribution into our nice simple Gaussian distribution. You could, of course, ask the question, what happens if the number of steps that we allow gets arbitrarily large? What happens if it goes to infinity? And it turns out that this gets what are referred to as continuous time normalizing flows, where our distributions smoothly, in fact, continuously deform over time or over some deformation process from a simple distribution to a complex distribution. And this is actually exactly what was done. This is based off of the neural ODE's work that I suspect many of you are familiar with in a paper called Fjord, where we use ordinary differential equations as a form of flow. And so the forward transformation, for instance, looks like this, where we're integrating this differential equation H forward in time to some fixed point, and that gets us this sort of process where we smoothly and continuously transform a Gaussian distribution to something more complex. And the inverse transformation in this case is actually kind of nice, because all it is just the reverse simulation. Okay, so we're just simulating the same differential equation backwards in time with a different starting condition. Okay. Now, I'm not going to go too deep into the nitty-gritty details of these, but for the interest of time, because the change of variable formula in this case changes a bit. There's a kind of a continuous form of the change of variable, where what was the kind of log absolute value of the determinant term that we had before becomes this integral of the trace of the Jacobian of the differential equation. And it turns out this is a little bit tricky to compute efficiently. And so the kind of major contribution that makes this kind of work was this Hutchinson trace estimator that shows a way to get kind of an unbiased approximation of this integral relatively efficiently by effectively integrating a very low dimensional object along with the transformation. Okay. And this has been used successfully to kind of model a variety of distributions. They make for really, really fun, pretty animations. The original work was tended to be a bit slow. The simulation of the differential equations, for instance, can be very computationally expensive. However, there's been a lot of great work in the past year or two at different ways to kind of regularize neural ODEs generally that are starting to make these sorts of transformations much more practical. Okay. All right. So I need to kind of hurry along here just in the interest of time. I want to make a few more points that are kind of important in practice, particularly for images. So for training generative models with maximum likelihood, one thing that's important to bear in mind is that normalizing flows are a model of continuous data, right? So we have derivatives in there, so it's a continuous transformation, and we're assuming that these x's are continuous valued vectors. And there's a bit of a problem there for modeling images because pixel intensities aren't continuous, okay? The way that we represent them, pixel intensities are actually discrete. They've been quantized, right? So there might be some 8-bit representation of the red, green, and blue channels in our images, all right? And that can actually lead to some subtle problems if you're not careful when using these continuous density models to approximate these discrete distributions. And in fact, it can lead to a certain type of singularity. And what we really want to optimize is actually the probability of the discrete values here on the left, which is actually kind of, you can think of it in the case of pixel intensities as an integral over, so if we know that the values, if we see the discrete value of, 213 in an RGB image, that was effectively rounded there from anywhere from 212 to 213, or truncated there, quantized there from anywhere 212 to 213. So there's kind of that continuous interval of values that could have produced that. And so that's where our continuous probability density comes in. But our data is actually this discrete representation. Okay. And so in practice during training, we need to do what's sometimes referred to as dequantization to dequantize the data, which effectively is just adding noise, right? So if you think about taking your discrete image Y here, let's say, and we add in, to every image Y, we're going to add in some uniform noise that effectively makes our discrete values continuous, okay? And you can kind of think about it where if we have originally this discrete distribution here on the left, adding uniform noise is kind of spreading it out like this. So now we get these kinds of step-like functions, right? And so now this is the distribution that we're approximating. And this is actually, doing this is kind of not optional. If you don't do it, you will very likely run into all sorts of weird singularities and oddities in training. But of course, if you look at this dequantized distribution where we've added this uniform noise here, this is not a particularly natural distribution, right? It has these kind of, it's flat everywhere, and it has these kind of big step functions. And in essence, we're asking our nice continuous distribution to kind of approximate this thing. And so there was this work by Jonathan Ho and others, which pointed out that, well, we can view this as a variational approximation or variational bound on the discrete discrete density, and therefore we can learn the distribution of we can learn a variational distribution of that dequantization noise. And so as a consequence, instead of trying to get our continuous normalizing flow to map to this kind of very blocky thing, we can let it approximate this, right? Where we kind of effectively smoothed out these blocks with the variational distribution. Okay. There's a bunch of different common architectures for flows. I've kind of given you in this introduction some of the basics. So I've just kind of, the ones that I've kind of mentioned or alluded to throughout here. There's many, many more than this now, but these are very much the building blocks that people commonly use. So for instance, with the NICE model where they're doing ICA, effectively what they had was a additive coupling layer with some diagonal linear transformation mixed in. Real NVP, as I mentioned, added in the affine coupling with channel-wise permutation in the multi-scale structure. GLOW added in, instead of a channel-wise permutation, they did a channel-wise linear transformation. And then Flow++ here, which is the work by Jonathan Ho, added in this variational dequantization, as well as this mixture of log CDF coupling transformation, which is kind of a more complex nonlinear transformation. Okay, so we are at the end. So I hope this has kind of given you a good flavor for normalizing flows, a good kind of starting point to go off of. Are there any questions? Because I think what we'll do here is I'll take any last questions for this segment. I'm going to maybe give at least myself a brief 5-minute break to rest my voice and drink some more water before I'll come back and I'll talk a little bit more about some applications and some kind of other models of normalizing flows in computer vision. But are there any last questions before we take this quick break? And I'll just throw up this here set of references for people to look at. Again, the recording of the session will be posted eventually, and I'll put up a PDF of the slides as well at some point. Okay, let's see here. Taryn, okay, excellent. So yeah, I figured this would be a question because this is kind of one of the a little more subtle but important components of normalizing flow. So Taryn here is asking about if the dimensionality of X and Z has to be the same. That seems like our latent space is not terribly latent the way that we think about it. Yeah, you're right. In theory, our latent space is the same dimensionality as the input of the images. One of the interesting components, though, of that multi-scale representation that I was talking about, where you kind of split off components of the dimension of your input dimension, and you just stop translating them, is that the ones that have undergone the most kind of complex nonlinear transformations, those start to kind of intuitively represent the most complex kind of components of your distribution. Okay, so you can one is you can still do interpolation in the full latent space, but those dimensions of the latent space tend to be things that are more kind of more semantically meaningful, for instance. The other thing that I'll add, though, is when we think about things like flows in contrast to GANs and VAEs, where you typically have a relatively low dimensional latent space, one of the challenges with both of those models is that you cannot always exactly reconstruct your any given image, right? So if I give you an arbitrary, if I've learned a VAE, for instance, of face images on Celeb A or whatever, and and I take some new image and I plug that in, there's no guarantee that I can actually exactly reconstruct that input image. Okay, so if I want to talk about manipulating images or compressing images or things like that, I've already introduced a form of kind of approximation there. And so the dimensionality, the invertibility here, I think is actually kind of intimately tied with the fact that we can really work with any image we want at inference time. Ulrich, you wanted to jump in?
Yeah, I would like to add two things. First of all, so working with a latent space that's as big as an image sounds like very expensive, but it's not without examples in deep learning in general. For example, if you consider a unit that, for example, is doing semantic segmentation, then the output is also an entire image. Or if you look at cycle guns, which, for example, turn summer images into winter images and vice versa, or day images into night images. So that's also very common to work with outputs that are as big as the input. So of course, your graphics card needs to be big enough to do it. Then there is the question by Kaushik. Is there a relation to image compression or data compression? I will come to that question in my part of the presentation. Though the short answer is that so invertible networks perform lossless compression in contrast to autoencoders, which compress lossy. Yeah? So you can compare it for images to PNG versus JPEG. Yeah, but the good thing is that, and that's a hot research question, we can structure the latent space such that we can drop some of the dimension, which only encode unimportant image content. And then we get what we call an artificial bottleneck or an artificial compression. Yeah, in practice, you set some dimensions of the latent space to 0 and then transform the image back. Yeah, and then if the dimensions have been chosen well, then the resulting image is indistinguishable from the original. That's also possible. And that's what I call the fundamental disentanglement. So a disentanglement of the latent space into important stuff and unimportant stuff.
Yeah, great. Yeah, that's yeah. There is a lot of work on if you're thinking about compression, one of the kind of from an information theoretic perspective, what you need to build efficient compression schemes is knowledge of your data distribution. And arguably what a normalizing flow does is it takes some very complex data distribution that we don't really know very well and transforms it into a normal distribution, which we know particularly well, right? And so I think there's actually some nice parallels here, and I'm glad Ulrich's going to be talking about some of that work on compression. Let's see here. So Moritz was asking intuitive way of assigning semantics to individual latents. So such as class labels and classification tasks. So absolutely. There's a bunch of different ways to think about this. There's been some work on, for instance, well, actually in the original Glow paper, they played around a little bit with the idea of using a Gaussian mixture model in the latent space, where the component of the mixture model you land in is connected to the label of the image, right? And in some sense, I think one of the cool things about flows is that we have this freedom to choose the structure of the latent space ourselves. And so we can impose semantic structure on the latent space ourselves and try to learn a transformation which will then kind of map to that semantic structure in the latent space. Carlos is asking about flows combined with implicit representations for natural signals. So there's actually an excellent paper on this recently, which I'm going to blank on the name. It popped up on Archive maybe a week or two ago. Sorry, a month or two ago, where they learn generative models of the weights, in essence, generative models of the weights of something like a siren or Fourier features network, to basically learn a distribution of continuous functions, which is kind of some really interesting work. In that case, they were using GANs, but in principle, I don't see a reason why you couldn't use flows. Okay. Okay, so I'm going to step out for just 1 second. Ulrich, I think Kaushik was following up with something, but maybe we'll take like if you wanted to answer that, and we can just take a quick 5-minute break, and then maybe at 11:30 Eastern. So in about 5 minutes, we'll pick up with the other half of the talk.
Yeah, I can answer Danya's question in the meantime. So he puts forward the idea to repeat. If the two ends of the network have different dimension, to repeat the smaller side sufficiently often, so to make up for the missing dimensions. Or another idea would be to zero-pet these dimensions. And the problem with that architecture is that if you run the network in reverse, then there is no guarantee in general that this pattern that you imposed on the space will actually occur. So let's say we transform Z to X and then have repeated Z several times to get the desired dimension. And then we take a different X and transform it backwards. So then the Z space, the Z representation that will come out will generally not have repeated dimensions. Yeah, because that would require the network architecture to follow some very strong restrictions that we cannot enforce by simple means. That said, so let me use zero padding because it's simpler than repetition. That said, when we zero pad and the inverse transform gives values close to zero in the dimensions that are supposed to be zero, then it might still be good enough. Yeah, so, and that indeed often happens, but we lose the theoretical guarantees of invertibility and so on. So that's the answer to Danya. Then answer to Kaushik, setting some latence to zero would make the transformation lossy. Exactly, that's the point of doing it. And the art is to disentangle the latent space such that setting them to zero does not change them very much. So we need to figure out which latent dimensions are important and which are not. Yeah, and I will say something to that problem in my part of the talk. And same to answer to Moritz. So I will say something about interpretation of the latent variables or class labels in the latent space in my part of the talk.
Okay. So I've gotten a brief stretch of my legs and a rest of my vocal cords. So I think we, in the interest of time, we'll go ahead and kick off here as people, filter in and out. Let me just need to share my screen again. There we go. Okay, so for the next 30 minutes or so, hopefully 30 minutes or so, I want to keep it there so I can make sure Ulrich has plenty of time, because there's lots of cool things to hear about from that. But I wanted to spend a little time talking about some work that I've done, two different examples that I think are kind of interesting or relevant for people in computer vision to know about with regards to normalizing flows. I want to recognize that this is actually kind of a really active area right now. It's actually really exciting and kind of fun to be in, because there's just tons of papers coming out. So for instance, this is a probably incomplete list of papers that I've put together from CVPR 2021 that are using normalizing flows or invertible neural networks. And I say incomplete because I haven't actually had a chance to read all of the papers for CVPR. Of course, I don't know anyone who does. And I found this list mostly by going through and looking for papers that had the word flow or invertible in the title, and selecting the ones that actually were doing things related. But this is just to say that these models are starting to become relevant in a lot of different areas and a lot of different applications, and that I think is kind of very exciting. So be sure to check out lots of these other applications of normalizing flows, and hopefully the introduction and the rest of the tutorial will kind of give you some good a good starting point for this work. Okay, so I'm going to talk about two different projects. And the first one is something called noise flow, noise modeling with conditional normalizing flows. This was work done when Abdul, the first author here, was an intern at Borealis in collaboration with Michael Brown, who was his PhD supervisor. And I like this project, and I like talking about it because I feel like it's a really good example of what you can do with flows. One of the things I'm really kind of interested in is how we bring relevant domain knowledge into a lot of our learning scenarios in computer vision, because we know a lot about the way the world works. We've spent, computer vision researchers have spent, 70 years or more trying to understand, the way images relate to the world. And we understand a lot. We understand a lot more than people might realize. And it would be great if we can actually put that to use in the context of our deep learning systems to kind of make them more robust, to make them more interpretable, to make them require less training data, and so on. Okay, so this project was looking at camera noise. And, when we take a picture with a camera and we feed it into our algorithm, we typically, we get an image out that maybe looks something like this. But these images are actually corrupted by noise. Okay, so for instance, we can kind of zoom in here on this part of the marker, and we see this sort of noise pattern in the intensity. And it turns out that accurately modeling this noise can be an important step to improve a lot of tasks in computer vision, as well as just being a task in and of itself, like denoising, right? But it is relevant for things like multi-image super resolution and so on. Okay. So if we take an image and let's say we do a really long, careful exposure, or we take lots of images, we can get a clean image, and we can subtract that clean image off from our noisy image. And now we're left with what is, in essence, the noise. And at first glance, at kind of initial inspection, this might appear to be just kind of simple white Gaussian noise. But if we actually look at a histogram, it's not. It's definitely not Gaussian. It is roughly unimodal, but definitely not Gaussian. And we can see that pretty clearly just by plotting over kind of the best Gaussian fit to it. Okay. But if we go back and we look at this noise, okay, let's say we just scale it up so we visualize it a bit better, and what we start to see is there's structure in this noise. Okay, it's not independent at every pixel. There's definitely structure, and that becomes really clear if we overlay it back onto the original image. We can see that the structure in the noise is actually related to the underlying intensity of the images that we're observing. Okay, and this is, as we would expect, this is what's referred to as signal-dependent noise. And this is exactly what you'd expect from physics based off of a Poisson model of photon count noise, where the variance should scale linearly with intensity. And in fact, if we actually do that, this is what we see. There's this nice fit of variance as a function of underlying intensity. And so this is actually a pretty good model, a reasonably good starting point of model, but it doesn't actually capture everything that's happening in a camera, okay? And so there's lots of other phenomena that are happening in cameras. We have things like the dark signal. So if you take a picture in a completely dark room, you don't actually get a completely black image with cameras. There's noise that comes from the electronics. There's fixed pattern noise because of errors in the manufacturing process. There's noise that's added because of the gain or the amplification of the signal. There's clipping, there's quantization, there's defective pixels, lots of things that are going on. In fact, the whole pipeline by which scene radiance, which is the thing that's corrupted with this kind of photon noise, or what's sometimes called shot noise, the whole pipeline by which that gets mapped into the RGB image, even the raw RGB image that we get, is actually a really complex kind of nonlinear pipeline. And so the motivation for noise flow was to say, you know, it's really difficult to construct accurate models of this pipeline and accurate models of this noise. And in fact, most people in practice, when they say, okay, I want to add realistic noise to my image, what do? They just add Gaussian noise. And as we've seen, Gaussian noise is not an accurate approximation. So the motivation was to say, can we learn a model of camera noise that is more accurate, maybe exploits as much information and as much knowledge about this pipeline as we have, but it's still going to be easy to use. And so in terms of a normalizing flow, means we can compute the likelihood, the density efficiently, and draw samples from it efficiently, okay? And so that is the model noise flow. And so what we did was, I'll show you how we construct some of these flows. So we start off with Gaussian noise, like we do with flows, as we've seen in the first part of the tutorial. And we're going to add in this signal dependent layer. Okay, so the signal dependent layer is going to be an invertible transformation of that Gaussian noise Z, and it's going to be conditioned on the clean image. Okay, and so here's our transformation. Let's just call it G of Z. Okay, and it's just going to be an element-wise scaling where the scale factor is going to have this particular form, square root of beta 1 times the clean intensity plus beta 2. Okay, and this actually exactly corresponds to this kind of signal dependent variance, or linearly dependent variance model that we saw before. Okay, now if you remember back to that diagram before, though, after we get that photon shot noise, there's a bunch of stuff that happens. We have readout, we have electronics that are going on in there, and we don't know how to model those things well. And so what we're going to do is we're going to just stick in some of these kind of normalizing flow, these more powerful normalizing flow pieces. So we're going to put in a couple of affine coupling layers, a couple of 1x1 convolution layers. And we're going to stick those in there and until we get to the next block, which is gain or amplification, right? So the ISO setting of a camera, which further amplifies noise in a somewhat predictable way. And so we're going to add in this other invertible transformation, which is actually going to, again, be a linear scaling, but it's going to be a linear scaling which will be dependent upon the ISO setting of the camera, as well as the particular make or identifier for a camera, because some cameras will have better noise properties than others. All right. And then again, after the gain, we have things like the analog to digital conversion, we have quantization and a whole bunch of other things that kick in there. And again, we don't necessarily know how to model those conveniently. And so we're going to throw in some more of these kind of black box normalizing flow pieces in terms of a bunch of affine coupling layers and 1x1 convolutions. And we're going to hope that that the output of all of this is going to be something that looks like realistic camera noise. Okay. Right. So this is the basic noise flow model. Okay. All of these pieces kind of stuck together. And the one thing that's interesting I'll point out is that the model that we actually used in practice has just under 3,000 parameters. Okay, which compared to, let's say, the 2 parameters that we see in the signal dependent model, beta 1 and beta 2, is quite a lot, but compared to a lot of deep learning models is relatively small. Okay, so we have this model, it's relatively compact. It incorporates a lot of domain knowledge, but the question is, how do we test it? How do we evaluate it? How do we train this model of camera noise? And that's where the smartphone image denoising dataset comes in, SIDD. This was a meticulously collected data set of clean and noisy pairs of images that were captured with smartphones. If you think collecting this data is easy, I encourage you to go read the paper. It's not. It turns out that, especially if you're trying to capture images with smartphone cameras, they do all sorts of things like optical stabilization that you can't turn off, which means that every frame is just a slightly jittered version. And so, you have to do all sorts of subpixel alignment, and you have to correct for fluctuations in lighting in order to get this to work properly. It is a really hard task. But Abdul did all this work and came up with this really nice, beautiful data set, which was just perfectly made for training something like noise flow. And so let's just take a look at some results here. We can compare this against kind of some different models of noise. Something called the camera noise level function, which is basically that kind of just linearly dependent, signal dependent Gaussian noise model. There's IID Gaussian noise. That's all of these being fit with maximum likelihood. And then there's noise flow. And so those are the patches that we're looking at kind of left to right here. And then the clean underlying image patch is shown on the right. And we can evaluate and compare these models using a bunch of different metrics. So for instance, we can just look at the negative log likelihood, and we see that we have this is negative log likelihood per dimension, I should add. But we see that we have a very significant improvement over the Gaussian model, and as well as a pretty significant improvement over just that simple heteroscedastic Gaussian model, or the camera noise level function. We also looked at some other metrics. This is this marginal KL here, where we also did quite well on, but I'm not going to go into the details of that. But one of the cool things that we did with this, and I think this is probably my favorite result in the whole paper, and actually one of my favorite results of any of my papers for a little while, is we used this model to train a denoiser. Okay, so if you think about training a denoiser, what are you doing? You're trying to take a neural network that takes as input a noisy image and spits out a clean image. And there's lots of different ways that you can imagine doing that, right? So you take a bunch of clean images, and maybe what you do is you add Gaussian noise to it, okay? And you train a denoiser to do that. And if you do that, then you can measure the reconstruction accuracy of the PSNR, and you get something like 43 decibels, which is actually pretty good. It's not terrible. Now, but that's using just IID Gaussian noise. And if you remember from the previous slide, IID Gaussian noise looks nothing like real noise, okay? It's just visually, obviously not the right kind of noise. So if we use the heteroscedastic noise, we get a bit better. We get another 1.5 decibel improvement on denoising using the camera noise level function. And if we use noise flow, we get a very significant improvement in the reconstruction quality in terms of PSNR. Now, all of that's great. This is your standard, we get the bold number on the table sort of thing that you put in your papers to get reviewers to like it. But the cool thing, the part that I really like about this result is this last line. It's called real. Okay, so these first 3 numbers were produced by taking the clean images in our data set and simulating noise. So we were simulating noise from a Gaussian distribution, simulating a noise from the camera noise level function, or simulating noise from our trained noise flow model. Okay, but of course we have a bunch of clean and noisy image pairs that we could just use to train the denoiser directly. And that's what that last line is. That's what real is, okay? And in this case, we actually get worse PSNR by using the data directly to train a denoiser than by using our trained noise flow model to generate noise and train the denoiser that way. And this should surprise you at least a little bit and make you a little bit curious and suspicious, because we're generally, it is kind of a dogma of machine learning that if you train directly on the data, you shouldn't be able to do better than that. And that is mostly a true sentiment. But what's happening here is that by virtue of being able to simulate noise, we're actually able to show the denoiser many, many more samples of what noise looks like. And because the noise flow model is actually fairly accurate, we're not leading it in the wrong direction. Because notice that real there, training directly on the data, is doing better than either the Gaussian model or the camera noise level function, okay? And the other kind of explanation for this somewhat unintuitive phenomena is that when you train a denoiser, you're training it to do more than just identify and understand noise. you're also training it to understand what real images look like, okay? And so as a consequence, we're able to give it kind of many more examples and kind of separate out what the real image looks like from the noise by being able to synthesize many examples of these noisy images. So let me just wrap here and I'll get to your question in a minute, Benoit. So in short, noise flow is kind of a realistic, right? We've encoded a lot of domain knowledge into this structure and practical model of camera noise for real images, okay? Now we capture, we use kind of domain knowledge to guide the construction and build kind of these specialized conditional flow transformations to capture things like signal dependence, the ISO settings, and camera specificity. But we use these kind of more general normalizing flow transformations to learn other aspects that are either unknown to us. We might not exactly know what's happening in hardware on a particular camera, or they might be very difficult to model. So if you want the full details of this, you should check out the paper. This was at ICCV 2 years ago. And there's lots of kind of cool things that we're thinking about. I'm still kind of working on this. Abdul's been hired at Samsung, and there's some fun projects continuing this work based on that. Benoit is asking whether noise flow is more computationally efficient than a CNN. So Benoit, it's important to recognize noise flow is a model of camera noise, whereas the CNN, like DNCNN or UNet, is an architecture for denoising. So we were using the noise flow model to generate data to train a DNCNN, or you could use any other denoising architecture. We use DNCNN simply because it was just kind of a standard denoising architecture. And yes, this is what I was referring to earlier when I mentioned flows can be linked with natural processes, right? So the more that we know about the process that generates our data, we might be able to incorporate those sorts of transformations directly into the generative model that we use. Okay. So Duchamp is asking if the distribution used to dequantize the data affects the ability of noise flow to capture the camera noise. So the nice thing about this particular application is that because we're working with raw images, we are actually working with more or less continuous floating point values, and so we didn't actually have to worry about dequantization. I'm looking. One of my students is looking at an extension of this to sRGB, so kind of more standard 0 to 256 kind of ranged, discrete ranged RGB values. And indeed, one of the trickier parts there is how to do the dequantization appropriately. Okay. Okay. Using noise flow to insert noise into synthetic data. Well, so actually there is one of the papers that I listed for CVPR this year, I should point out, is actually using something, it's not using noise flow, but it's using normalizing flows to learn more general forms of image degradations. Actually, yes, Stasios, you are kind of reading my mind a little bit. I have another project with a different group that is starting to look at noise modeling for hyperspectral imagery, but it's very nascent, and I'm very keen to work on it. I think it's a great application. I think using these sorts of models for cameras, we understand camera noise pretty well. I think actually the beauty of this is actually other sorts of measurement devices like hyperspectral cameras or things like that, where we know maybe even less about the data kind of generation process. Yeah, Ulrich.
I just want to add, so one major application of multispectral data is astronomy, where it's about the only thing that we can ever know about the universe, apart from theory. And normalizing flows have been successfully applied in order to interpret the observed spectra of stars, for example. So, for example, to solve the problem of the age of the star and of the mass of the star, just by looking at different colors in the telescope. And I will also show a little application with multispectral data later in my part.
Great. Yeah, thanks, Ulrich. Yeah, it's. I think a lot of this stuff is hyperspectral imagery and astronomy and physics and a lot of these kind of scientific applications are really, you know, I've also worked on like electron microscopy, and so I'm also kind of interested in using these types of models to model that data as well. Okay, so I'm going to move on in the interest of time. If there's more questions or if you want to follow up on any of these topics, feel free to email me afterwards if I have to rush through and I can't get to your question though. So the next project, the last project that I'm going to talk about before I hand the reins over to Ulrich here is Wavelet Flow. So this was a paper at NeurIPS last year. This was my student co-supervised with Costa Drapanis, Jason Yu. He started this actually as an internship at Borealis. And it went on to finish it for his master's thesis. So one of the challenges that we were looking at, two things really. One was that normalizing flow models can be quite large. So the GLOW architecture I mentioned, one of the things that they did to make GLOW successful was they just trained it bigger and longer. And so, you know, the biggest models that they had took about a full GPU year of training to compute at a resolution, to train at a resolution of 256 square. Okay, so these are very big, very heavy, hard, you know, models, for instance. And one of the other challenges is that they're not scale consistent. So for instance, you can take a GLOW architecture and train it on a 256 square image and then tweak it slightly and train it on a 128 square image data set, exactly the same data set, just downsampled, and you can get dramatically different results. And this kind of bothered me, and it got me thinking with my student Jason and collaborator Costa about scale structure and generative models broadly. And so existing normalizing flow architectures before this work really lacked any sort of explicit notion of signal scale. Now this is, to be clear, this is distinct from the kind of multi-scale models, what are referred to as multi-scale models that have been used in real NVP. And because those are really, as I mentioned, talking about kind of scale of complexity of the distribution, as opposed to scale in kind of the computer vision sense of the signal, right? The resolution of the signal, right? And so we get phenomena like models being trained at different resolutions are consistent. We have that training very high res models can be extremely expensive. And so we were thinking about this and we wanted to figure how can we handle this better in flows? And people have explored this in other generative models like GANs and VAEs, where people have done things like exploit image pyramids, for instance. Or do like progressive, you know, there's like progressive GAN and a bunch of other things that have looked at, you know, generating using image pyramids and things like that to handle signal scale in the generative model. Okay. Now, the image pyramids have a very long and successful history in computer vision. So you could say, well, why don't we do that too? Why don't we also just use image pyramids? And one of the problems is that an image pyramid is an overcomplete representation of an image. Okay, what that means is that that dimensionality constraint that we kind of have with normalizing flows isn't exactly satisfied. And you know, there might be some ways to kind of work around that. But we said, well, could we find another representation which would allow us to kind of represent scale in a nice way, but it isn't overcomplete and kind of meshes more naturally with the framework of normalizing flows. And so that led us to wavelets. Okay. Now, some of you with a signal processing background might be familiar with wavelets, but just in case you're not, let me just walk through really quickly how they work. So if you take an image like this and you run it through a wavelet transform, what that's going to do is it's going to spit out kind of two things. It's going to spit out an image at a lower resolution, let's say half resolution, and it's going to spit out what we'll call detail coefficients. And these detail coefficients are kind of, they're exactly what you need to reconstruct the high res image in conjunction with the corresponding lower resolution image. Okay, and if you want to kind of be particular about this, we can do things like count the dimensions here. And so if our original image is n square with 3 channels, the resulting low res image is going to be n over 2 square with 3 channels, which is effectively just going to be a blur and downsample, okay, or a low pass filter. And then the detail coefficients are also going to be n over 2 square, but they're going to have 9 channels. And if you count and check the dimensions there, you'll see that everything matches up, and we're actually preserving all the dimensionality. In fact, we're preserving all the information in that original high resolution signal. We're just splitting it into these 2 pieces: low res image everything else in essence, okay, the detail coefficients. And you can continue and you can apply this process again, and now you're going to get a lower resolution image that's now n/4 square and another set of detail coefficients, okay? And the wavelet transform has this property it's invertible, right? So we can take, if we preserve just the detail coefficients and the lowest resolution image that we have, okay, we can use the inverse wavelet transform to reconstruct the next higher resolution image along with the detail coefficients. And now we can use the next set of detail coefficients again with the inverse wavelet transform to eventually go all the way back to our full high resolution image. Okay. So this is the wavelet transform. I guess I should strictly say the discrete wavelet transform. Okay. Now, formally, we can kind of express this in the following way, which is that if we do that wavelet transform process, we can represent the wavelet transformation as this function h, which takes in an image and spits out whatever that lowest resolution image that you're gonna keep is, and then all the detail coefficients along the way, right? So we have some s stages, d0 up to ds, and we have our image at the lowest resolution I0. And that is what I'll refer to as kind of the wavelet transformation. So a couple of properties of it. One is that it preserves dimensionality. If you want to check, you can verify that yourself, which means that it's potentially invertible. It's not guaranteed that it's invertible, but potentially it is. For a wavelet, it is linear, which means it's a differentiable function. So it checks that box. And in fact, it has a constant determinant because it's just a linear transformation. And in fact, if you choose the right type of wavelet, then we can show that our function h here is actually orthonormal, which means that the determinant of the transformation is actually going to be 1, which guarantees that it's going to be invertible. And all of this kind of says that a wavelet transform of an image is going to work very, very nicely as a type of normalizing flow. Okay, so just as a detail in practice, we use an orthonormal form of the Haar wavelet, which is just a really kind of the simplest, most basic form of wavelet that you can have really. Okay, so what do we do with that? Well, the first thing we can do with this Haar wavelet transform is we can see what happens to a distribution over images when we transform it through the Haar wavelet through this wavelet transform. And again, we're just going to use the change of variables, which is where we started with normalizing flows. And what we see is we do the change of variables with this wavelet transform. And remember, I said if we have an orthonormal wavelet, then the determinant of the transformation is just 1. So the volume correction term disappears, and we're left with a distribution of the low res image and all of the detail coefficients. And now I can take this distribution and I can use the product rule of probability to write it or factorize it in the following way, right? So now I have the distribution over my lowest resolution image, and note that a lowest resolution image, this could be a 1-by-1 image. So this could just be a single color, okay? And then the corresponding detail coefficients at that level. And now the detail coefficients at the next level conditioned on the previous detail coefficients in the low res image and so forth. Okay, so this is just using product rule of probability to factorize this distribution. And now what I'm going to do is I'm going to use the fact that we can invert the wavelet transform, and we can invert it at basically at any level we want. Okay, and I can write this whole big product like this. Okay, so it's a distribution of the lowest resolution image, and then at every scale, I'm going to have the conditional distribution of detail coefficients at that scale, given the low resolution image at that scale. All right. So this is wavelet flow in a nutshell. Okay, we're going to take this wavelet transform, we're going to transform our images to get this detail coefficient and low res image representation, and now we can stick that in with some basic probability manipulations and the inverse wavelet transform, okay, in order to get to represent our distribution over a high resolution image as a product of all of these basic distributions of detail coefficients conditioned on the image at that resolution. And what does this get us? Well, one thing is if we do our training with maximum likelihood, okay, this is what the log likelihood of an image looks like under this model. Okay, so the log likelihood of our high resolution image I is just the log likelihood of the low resolution image I0, and then a sum over all of the log likelihoods of the detail coefficients conditioned on the corresponding low res image. All right, And what that means is that these distributions can all be trained completely independently of one another, okay? Because if I have my original high-res image, I can apply my wavelet transform and get all of the lower resolution images and all of the detail coefficients. And each one of these distributions can now be trained completely independently of one another, okay? And so in the paper, in practice, we used a glow-based normalizing flow architecture to represent these distributions. Please see the paper for the details. I'm not going to go into it now in the interest of time. But now with this wavelet flow model, if we look at generation, for instance, one of the things we can do, the way we generate an image is we sample from our distribution of I0 of our base image distribution. That gets us a low-res image. Now, given that low-res image, we're going to sample a set of detail coefficients at that resolution. And we apply the inverse wavelet transform to get the image at the next level up. And now we repeat the process. We use that image to sample a set of detail coefficients. We apply the inverse wavelet transform, and we can kind of iterate this process to get back to our high resolution, to generate an arbitrarily high resolution image, okay? We evaluated this model quantitatively on kind of the usual benchmarks. I don't normally like to show quantitative results this way. I feel like a table of numbers is actually a bit more expressive, but the point of this paper was not to try to beat either GLOW or real MVP. And indeed, what we find is that we kind of, we've normalized our models here for kind of complexity in terms of number of parameters. And we, roughly speaking, are on par with GLOW and real MVP, or particularly GLOW, for these different data sets, which is fine. One thing I'll note, though, is that Celebe high quality and Flickr Faces high quality, these two data sets down here, these are 1 megapixel data sets. And you'll notice there's no real MVP or GLOW bars, and that's because, practically speaking, training real MVP or GLOW on either of these data sets would be almost impossible, right? Because of how big those models would have to be to train on a 1 megapixel image, okay? And in fact, if we look at training time, for instance, so these are the training bars here. This is training time for GLOW versus wavelet flow. We get roughly a 7 to 15x speed up depending on the particulars of the data set to train our model. And because all of those models can be trained independently, we can actually parallelize the training much more efficiently. Each one of those models can actually be a fair bit simpler than and not nearly as deep as the full GLOW models. Some of the fun benefits of this model, you can look at this just as, well, this is another way to construct a very high resolution model of images with a normalizing flow. But because we're actually explicitly representing the wavelet, the scale structure of our images through this wavelet transform, we actually get the ability to do things, for instance, like super resolution for free. Okay, so this is just a 128 by a 128 square image that's been 8 times upsampled. And we can plug in a real image for any of those low resolution images in our sampling process. All right. And that allows us to do this sort of super resolution upsampling basically for free. We didn't train for this. We didn't plan for this. We didn't even try to compete for this, but it just kind of comes out. All right. So this is the upsampled image. Here's the original, particularly over Zoom. It's going to be hard to see the difference. So if we kind of zoom in here, we can see kind of on some patches, we can see kind of the naive upsampling approach versus upsampling with wavelet flow and the original. Okay. And so just to wrap up here, with wavelet flow, we get, each one of these distributions of detail coefficients can potentially be simpler, and most importantly, they can be learned independently, which allows training to be parallelized much more efficiently for training on high resolution signals. And I'd also note that I didn't talk about this too much, but if we train a model at 1024 square, in our generation process, for instance, we can stop generating at any given point, which basically means that we have built into our model of 1 megapixel images, a model of 512 square, 256 square, all the way down. We have every lower resolution image model that you want built into our high resolution image model just by stopping the wavelet transformation wherever we want, okay? Which allows us to do things like super resolution for free and so forth. A few last points just on this. One of the things I'm really keen on doing this at some point in the future, I haven't had a chance to, is trying to run it on other types of data. I think the efficiency of this wavelet representation is great for 2D images, but I think it would be even more important or more relevant for 3D data like MRI, CT, or actually potentially you could imagine doing this for hyperspectral imagery, since somebody else has already mentioned that. And of course, for full details, you can check out the paper at NeurIPS last year. Okay, so I apologize that I had to rush through at the end there. If there's any questions, I'm happy to take them now. Okay. Does the bottom level have to be a low resolution image? Basically, yes. So the wavelet flow, so a wavelet transform is really fundamentally about successively getting rid of high resolution information and then downsampling and only keeping low resolution information. So the bottom really is it has to be a low resolution image. Okay. So Ro is asking, the wavelet transform is a normal. Yes. So we are basically, so if you think back, actually, one way to understand what's happening in wavelet flow is to think back to the first part of my of the lecture where I was talking about linear transformations. So a wavelet transform is just another linear transformation. And so basically what we're saying is that if you do this very specific linear transformation of a wavelet flow, you expose all of this lovely scale structure of the underlying signal in the case of images or things like CTs or MRIs. And now we can learn our distribution just by learning different parts of this structure in terms of these distributions of detail coefficients given the low res image. Yeah, in essence, the splitting scheme actually kind of falls out for free here in a sense, right? We're not really doing splitting in the same way. Like, I mean, we are, like, one way to think about what the splitting that we're doing is that we are basically dividing our input dimensions into subsets that correspond to different resolutions. And now we can train each of those resolutions independently. Any other questions? Okay, so I'm gonna go ahead and stop sharing here in order to let Ulrich go ahead and get set up. But if you have other questions, please feel free to post them in the chat, and I'll be sticking around here for a bit as well if other questions pop up. And again, feel free to find me on Twitter or send me email or whatever if there's other questions or ideas or thoughts that come up after the fact. I'm happy to answer offline as well. Okay. Ulrich, do we want to take a quick break or do you want to just dive in the interest of time? I'll defer to you here.
Yeah, let's say we start at 6:15 our time.
Okay, so that's 5 minutes, right?
Time, I guess. 5 minutes, yes.
Yeah. Okay, so yeah, everyone, please, feel free to get up, stretch your legs, get some water, get a snack, get some dinner or breakfast or lunch, depending where in the world you happen to be. And we'll be back in 5 minutes. Yes, I'll be posting some slides online. They'll be linked and referenced off of the tutorial website when they're available. And we are recording this as well, so you can watch this later again if you wish.
Okay, let's start. Welcome all to the second part of this tutorial. And I will start with a short recap of the most important things that Markus has already shown you. So usually I give this tutorial without the great first part of Markus, and so I need to repeat something. So first, why is generative modeling so interesting? If you look at the deep learning success story so far, and look at a model that predicts some y's given some x's, yeah, then these models either give point estimates, so a single answer, or even a distribution of answers, but they mainly rely on what's called the discriminative paradigm or the transductive paradigm, which means that they try to answer the question as directly as possible without going the detour to first learning how the world works and then using that knowledge to answer the original question. But they try to answer the original question, so predicting y from x, as directly as possible. That's what transductive means. And it works very well, but it turns out that transductive models or discriminative models are very hard to interpret and very hard to explain, and also very hard to validate when they will break down. Yeah, consider autonomous driving, then of course the validation requirements are pretty extreme, and that will never work, I believe, with a transductive paradigm. In contrast, generative modeling tries to model the opposite conditional probability. So how do the x's, the complex observables, arise from the hidden variables y? Yeah, and then you can still solve the original problem by just invoking the Bayesian theorem. But it turns out that these likelihood models, how the data arise from the internal state of the world, provide a lot more insight, or at least have the potential to provide a lot more insight about how the world works than these merely discriminative models. Yeah, and to quote Feynman, he said, "What I cannot create, I do not understand." And create is synonym for generative. So we can create more data of the same kind as the real world because we have understood how the real world works. So here are the three major paradigms of generative modeling that Markus already mentioned. So the GANs are one way. Yeah, so you have a generator that can take noise and generate fake data that a discriminator has a hard time to distinguish from real data. But the other way around, to go from data to the latent space Z, is not implemented in these models. Yeah, and it's generally impossible or very expensive. In contrast, the autoencoders are round-trip models. So they have an encoder that transforms data to latent variables and a decoder that transforms back. And these are usually trained by their round-trip performance, so the reconstruction loss or the cycle loss between the original and the reconstructed data. And especially in the variational variety, you also have a model for the distribution of the latent codes. So when you sample from that P of Z, then you can also create fake data by using just the decoder. Yeah, and you can use the encoder to calculate the probability of the given X. And in terms of encoding, this is a lossy encoding because the dimension of Z is in general smaller than the dimension of X. So we have what's called a bottleneck on the latent side. In contrast, normalizing flows use just a single network, which is invertible. So running this network forward is the encoder, and running the network backwards is the decoder. Yeah? And since X and Z have the same dimension and the transformation is invertible, this is a lossless encoding if we consider the Z's as codes for the X's. Yeah, and the reconstruction is of course perfect. So there's no point in training with a reconstruction loss. So what we use is the change of variables formula that we have already seen multiple times today, and train with maximum likelihood loss. So here, the normalizing flow again, also an illustration that Markus already showed. So we have a base distribution in latent space, a simple one like the Gaussian, and we have a more complicated distribution in data space. So in this case, also a mixture of two Gaussians. Yeah, and when we consider the mass in the latent space as a pile of sand, and the mass in the data space as a different pile of sand, or in this case, two piles of sand. Yeah, then what we want to do is to take the sand from latent space and move it to the appropriate place in data space. Yeah. So we split the sand, the latent sand, and move it to the appropriate places and shape the distributions as desired. Yeah, that's what a normalizing flow is essentially doing. That's also why it is so closely related to optimal transport. Yeah, and just for terminology, we have the reference distribution in Z that we can choose more or less freely, then the target distribution in X that we would like to model. And then we learn this transport map. So the forward map is F, goes from X to Z, and the inverse map is G, goes from Z back to X, and is the inverse of F. And then we have the change of variables formula to calculate the probability density of X in terms of the density in Z and the volume correction term, or in mathematical notation, this is also often written as what's called a push forward from the Z space to the X space. And so this hash sign means that the transformation G pushes forward the latent distribution to the data distribution. So here are three possibilities to implement normalizing flows. We have already talked a little bit about autoregressive models, where you use the Bayesian chain rule decomposition in order to model the conditionals. So you condition each I on the variables with index less than I. And there is a theorem that this is essentially always possible. And then you get a Jacobian that has this full triangular form. Yeah, so the first variable only depends on a single latent variable, and the first latent variable, and then the second one depends on two, and so on. Yeah, and the problem with this is that it is only efficient one way. So the other way is expensive. So you can train two sibling models, one for the forward and one for the backward direction, and this works quite well. So the parallel wavenet for speech generation is an example for a pair of complementary autoregressive models. So then the invertible residual network is a modification of the standard residual networks in order to make them invertible. And then I will explain in a minute how this can be done. And the third is the real NVP decoupling layer design that we already heard a lot about. So let me start with the ResNets. And historically, the ResNets is the network type. So the invertible ResNet is the network type that first got me interested in this whole business of invertible networks. So the one that caught my attention. So just as a brief recap, what is a residual network? So a standard network would compute the next layer, ZL plus 1, by some nonlinear transformation of the previous layer, ZL. Whereas a residual network models the difference between the two layers. So the difference between ZL plus 1 minus ZL is a nonlinear transformation of the data at ZL. Or bringing the CL to the other side. So this is the formula. So, and when we write this diagrammatically, we have a skip connection and a processed connection, and then we have an addition of the two lanes. Yeah, and this has the advantage that you can build very deep models. So we have here the normal layers and then the skip connections on top of them. And the presence of these skip connections has the effect that the vanishing gradient problem does not occur as much as in normal deep networks. And so you can train deeper networks using this technique. But it's also quite expensive because you need to store the activations during training of the entire network. And here comes the RevNet, so the reversible residual net. And they noticed that a residual block on the left looks very much like a coupling block on the right. Yeah, or here, in fact, a pair of coupling blocks where the XA and XB lanes are exchanged in the second transformation. Yeah, and it's also just a linear additive coupling block because we only have a plus and not a multiplication as in the affine couplings. But otherwise, it's the same thing. So the lanes A and B are here called X1 and X2. And then their skip connection is X1, and then the is X2. And then the other skip connection is the result from the first. So the roles are exchanged. And the effect of this is, since the network is invertible, we do not have to store the activations during training, because we can reconstruct the activations when we need it for training, for computing the gradient, by running the network backwards. Yeah, and that's how it looks like. So the gradient step for a reversible residual net just consists of a few extra lines of code which reconstruct the activations by running the network backwards and then taking the usual derivatives using autodiff. Yeah, and the benefit is that you can train a neural network of about the same size and about the same performance using just a quarter of the memory in your graphics card. Yeah, and here you see how the training loss and the test loss behaves. So it's almost indistinguishable between a normal ResNet and a reversible ResNet. Here is, so of course there is a trade-off. So it takes longer to train because you always have to recalculate the activations instead of storing them. So here's a direct benefit analysis of a medical image data set. So, and the standard residual net can only work in 2D. So this image size is 480 times 320, 130 channels, but the depth is 1. And it can also only afford to have 40 layers. And already it uses up over 10 gigabytes of memory during training. So now using a reversible ResNet allows one to, where's my mouse? Allows one to use a much deeper network, 400 layers, and still use only a quarter of the memory. And finally, the 3D version of the whole thing can now process 32 layers of the data at once and still has a depth of 400 and still uses less than 12 gigabytes of memory. So that's what most advanced graphic cards had back then. Yeah, so you immediately see the benefit. Also, this has nothing to do with invertible networks, as Markus explained them. So there are a few questions. Let me look them up. So with GANs, is it possible to use an invertible network for the generator? Yeah, so all kinds of combinations that you can think of have essentially been tried by someone. So it's a combinatorial space of possibilities, and probably if you look carefully enough, you will find any combination. So is there any work on class conditional generative models? Yeah, that's what I will talk about later. And Markus already answered to this question. So now, can we take this idea one step further and make a really invertible network from it? So the RevNet was only to save memory, but now we would like to have a real normalizing flow. And there are three problems that need to be solved. So how can one ensure that the mapping is bijective? How can one ensure that the inverse can be efficiently computed? And how can one perform training, so maximum likelihood learning? Yeah, and here are the building blocks. So the first observation is that the mapping is bijective if the derivative is positive, and the generalization of this condition to multiple dimensions is that the Lipschitz constant of this G function must be less than 1. Yeah, so this is the condition, but the norm between the answers must be less than the norm of the arguments difference, the norm of the difference and the norm of the argument and differences. Yeah, this is called the Lipschitz bound, must be less than 0. And so one has to restrict the expressivity of G in order to make sure that this works. So also the second question can be answered very easily. So you can just calculate the inverse by some iterative process like fixed point iteration or Newton. So you initialize with the output of the layer and then compute the difference between the actual output and the forward mapping. And this gives you your next guess. And then you iterate this a few times, like 10 or 20, and then it converges to the input xt. So that's also very easy. And the more difficult part is now how do you restrict the G function to be Lipschitz. And a very simple strategy is if this is a ReLU network, then you just need to ensure, or something similar, you need to ensure that the linear part of the layer is Lipschitz. And this is the case if the largest singular value of the weight matrix is less than 1. And they ensure this, the inventors of this method, by just computing the largest eigenvalue and dividing by it. But this is too expensive to do exactly, so they just do one iteration of power iteration, one step of power iteration, and that gives an approximation of the largest eigenvalue, and then they divide by that approximation, and that turns out to be good enough and very cheap. Another thing is that it turned out that the ReLU activation is not the best choice, but the swish activation is much better. So the swish is R times the sigmoid function. And then they have extended it to the lip swish, which scales the function a little bit down so that it actually has a Lipschitz constant less than 1, because the original swish is a little bit too, as a derivative, a little bit too big. And the benefit of this is that when you want to train, you need the gradient of the Jacobian matrix. So the Jacobian is the first derivative, and the gradient of the first derivative is a second derivative. Yes, so your network should have good second derivatives in order to be trainable. And this Lipschitz, this lip swish function improves the second derivative of the network. So, and finally, how to perform maximum likelihood training. So the main question here is how we determine the log determinant of the Jacobian. And there is what's called a truncated power series estimator. So essentially you sample random vectors V and then multiply with the Jacobian to some power and take the empirical average of this. And this gives a reasonable estimate of the Jacobian. Now, if you are interested in the details, you have to read the paper cited down here. Yeah, there may be a better solution that I will skip now. And as you see here, seeing the numbers, so it's a bit better than other normalizing flow methods. So the residual flow is the degeneration of the IRSnet from 2 years ago. So now coming back to the coupling design, we already have seen these coupling layers. So we split and then have the two outputs and have the two internal networks S and T, which compute the coefficients of the linear transform. Yeah, and then so here's the computation. We first split, then we compute the coefficients. So this is the purple arrows. And then we transform the upper part that gives us the red result, and then we merge, giving us the red output. And the inverse is very simple, just running it backwards. So we split again, compute the purple coefficients, and then invert the red arrow in a green arrow, and then merge the result, and that gives us back our input. Yeah, and the important thing here is that the nested functions S and T are in both cases run in the same direction. So they do not have to be invertible themselves. Yeah, and so can be any function, and typically are neural networks or convolutional neural networks if we work with images. So, and then since a single layer is not very powerful, we stack them into a deep network, and to make sure that the skip connection is not always the same set of coordinates, we shuffle the coordinates around between coupling layers by some permutation matrix Q, or Q can also be any orthogonal matrix. So orthogonal matrices are good because they are easy to invert, because the inverse is just a transpose. Yeah, and they also have a very simple Jacobian determinant, which is just 1 by construction. And then the logarithm of the Jacobian of Q is 0. Yeah, so this has no influence on the entire volume correction. The volume correction only comes from the coupling layers. And surprisingly, this simple architecture with affine couplings and random permutations or random projections gives quite good results. So every once in a while, the reviewers tell us that the coupling architecture is not state of the art because it's not as complicated as alternative architectures. But in fact, if you train it carefully and if you design it carefully, its results are as good as any other normalizing flow architecture we know of. Yeah, the only problem is that on two-dimensional toy problems, the coupling layers are bad, and because you have not many opportunities to split 2 dimensions into 2 halves. Yeah, and there so on the toy problems, other architectures are often better, but if you come to the real thing, then there is no big difference. So, and I also already said this, that it is similar to an autoencoder, that the forward computation is the encoder, the backward computation is the decoder. And the difference is that we have a lossless encoding. So there is a question in the chat. I know it just says thanks. Okay. So now, again, for the training, so we have the parameters from the whole thing and the change of variables formula. And then we take the negative log likelihood of the change of variables formula. And then we get the logarithm of the reference distribution in the Z space and the logarithm of the Jacobian determinant. And if this orange distribution is standard normal, then the logarithm is just very simple, e over 2 times the logarithm of 2 pi plus 1/2 the squared norm of the function value in Z space. And the logarithm of the determinant is also very simple because it just reduces to a sum over all the coupling layers. So L runs over layers. And then we take the logarithm of the S coefficients, so element-wise, and then sum the logarithms up. And that's all. Yeah, and you see this is a very simple loss function that is also very easy to compute the gradient of. As I already said, the Q has no influence because its log det is 0. By the way, these are all different Qs, not the same. Yeah, and that gives us the opportunity to do maximum likelihood training. So this is again the negative log likelihood from the previous slide. And now we want to minimize the negative log likelihood of the training set. So we take the argmax over theta of the probability of the training set. And since the training examples are IID, this is just the product over the probabilities of each example. And by taking the logarithm, it's the sum over the negative logarithms. And then we can insert our negative log likelihood and end up with this loss function. So we take the sum over all training examples of the squared distance in Z space and the negative sum of the logarithms of the scaling coefficients. And intuitively, what this means is that the first term, the orange term, tries to pull the latent codes. These are the latent codes towards the origin of the latent coordinate system. So if we had only the orange term, then the optimal solution would be to map all the data to 0, because that has the smallest loss. But of course, that's not what we want. And this volume correction term has the effect that the volume, if the volume of the data shrinks, of the data distribution shrinks, then it gets expensive. So moving all the latent codes to 0 is very expensive in the second term. And when the two terms are balanced, we find our optimal solution. And this is the Gaussian, the standard normal latent distribution. So this is my brief recap. So if there are questions, it's a good time to ask now. And now I will start with new material. Okay, there are no questions so far. So far I have explained how to model just the joint distribution of X. But in practice, we often need to model conditionals, P of X given Y or P of Y given X, either way. Here are two examples. One is generative classification, where the X's are features and the Y are the corresponding class labels. And we would like to estimate the posterior of the image of the class given the image using Bayes' rule. So this posterior is proportional to the likelihood of an image given its class times the prior of the different classes. Yeah, and what we use the invertible network for is to learn this likelihood function of likelihood of images given the class using a conditional INN and specifically a information bottleneck INN, which I will explain shortly. Another application is to solve inverse problems. In that case, X are hidden system parameters that we would like to estimate. So our system properties that we know exist, but are hard to measure directly or impossible or too expensive. And Y are observable quantities that we can easily measure. Yeah, a typical example would be Y is a spectrum that we can take from a microscope or a telescope, and X are the properties of the tissue that we look at or of the stars that we look at. And in this case, we would like to determine the posterior of X given the observations Y. Yeah, and here in this case, we would also would like to learn the probability of X given Y. And I will also shortly show how we can do that. So since we are now talking about conditional inference, we need to look at how can we extend the invertible neural network in order to accommodate this requirement. And one possibility is to split the latent space into two parts, Y and Z, like here. And Y are the observations, and then Z are three latent variables, which together add up to the same dimension as X. Yeah, so the intuitive meaning is that the transformation of X, so the hidden state of the world, to the observations Y loses information. So Y does not have enough information to fully recover X. And then the Z's collect all the lost information. And I will show a toy example later to make clear how this works. Yeah, so Y and Z together have the same information content as X because the transformation is invertible. So another possibility is what's called the latent mixture invertible network. In that case, the latent distribution is not a standard normal, but a mixture of Gaussians. And this is, of course, especially useful if the conditioning variable Y is discrete, so class labels, for example. In that case, we just have one mixture component in Z space for every class label. Yeah, so here we have two class labels and two mixture components. And then the invertible network will still map from X to Z, but now the training will take into account the fact that Z is a mixture distribution. So it has to optimize not just the function, the mapping f of X gives Z, but also the parameters of the mixture distribution. So the means and the variances of the mixture components. And this architecture is especially useful for classification, generative classification, and disentanglement. So, and the third one, the conditional invertible network, is especially useful for inverse inference. So here, we add additional input to the invertible network, and I will show on the next slide how this is done. So the function, the mapping from X to Z now also depends on Y, and the inverse mapping from Z to X also depends on Y. Yeah, so Y is an input regardless of direction of the network. Yeah, and this also gives us then a conditional probability. So we have a conditional probability in all three variations. So let's first look at the conditional INN, so the right one in from the previous slide. So we want to model the probability of X given Y, and we reparameterize this as a deterministic function G of Z given X parameterized with Y. G of Z and Y gives X, and then Z is taken from the latent distribution. Yeah, and then the forward process is inverse. So f of X and Y is the inverse of G in the first argument. So the function f is only invertible in the first argument. And then the minimum log likelihood loss is just changed a very little bit. So the function f now gets a new parameter y that is put here, and the interior networks S also get the new parameter y. Yeah, so that's all what changes in the training function from the previous slide. And in practice, what you do is you take the y's and just feed them into all the internal networks of the coupling layers. And optionally, you can first pre-process the y's when they are very complicated. So if the y's are class labels, you would feed them directly to the internal networks. If they are images, you would first run them through some feature detector in order to condense the image information. Otherwise, the S and T networks would have to be very big to do that on their own. Okay, so now this conditional INN allows you to turn each deterministic network easily into a probabilistic network. So here is a deterministic network. So it could be a standard ResNet or VGG or whatever. So it takes Y. So in this case, Y is the image. Y is the image, and then X would be the class label, and the network gives out a single output. Yeah, it's a deterministic network, and you train it by minimizing, for example, the squared loss between the network output and the true value of X. So now you can take these networks and cut off the final layers, one layer or several layers, and then this is done very often, and then the remaining network can act as a feature detector. Yeah, so we call the output of this smaller network C, and C are the learned features from Y. And now we attach a conditional INN to the output. So the C's become the condition of the INN, and then the INN learns a mapping between the output X and the latent space Z. And this is then a representation of the conditional probability X given Y, because the condition depends on Y deterministically, and the reparameterization into this decoder function G of Z and the features gives us the desired push forward when Z is sampled from the standard normal. And this also changes the loss function for training. We can now use maximum likelihood loss. Yeah, we train the G, the push forward function, the transform, and the H, the feature detection function, by maximizing the log likelihood. Yeah, and arguably, this is more general because the log likelihood is a quantity that's defined independently of the application, whereas the squared error makes only sense for particular applications. So now let's look at a concrete example. Let's take colorization as an inverse problem. So the forward process is decolorization. So we remove color, which is very simple by just taking a color image and making it grayscale. And this is especially simple if you represent the image in what's called the LAB color space, because then the L channel is the gray information, so the brightness information, and A and B contain the color information in that particular color space. And so the forward process is to transform the image into the LAB color space and throw away A and B. And then you get a grayscale image. And the inverse problem is now, given the grayscale image, to guess what plausible color channels are. So we would like to recover the A and B channels. And then if we combine the recovered A and B channels with the given grayscale channel, then we would get back a color image. And then the question is, how can we make the color image as realistic as possible? Yeah, and this type of problem has been addressed with deterministic networks like a UNet in this case. So we feed in the color image and then processes in a multi-scale manner. Then we get a latent space, and then we go upwards, so our feature space, and then we go upwards in resolution and get out the color channels. And then when we combine these, we get back a color image. Now I said we can cut off part of the deterministic network. That's what I do here. So I just take the encoding part of the UNet and use it as a feature detector for a conditional invertible neural network. So on the right-hand side, we have the conditional invertible neural network, and the features of the grayscale image are fed into the different coupling layers of this invertible neural network. And then, given noise in the latent space and features of the grayscale image, it will produce color channels that we can combine with the grayscale channel and then get a color image back. The main difference between the original deterministic network and this CINN design is that by using different noise instantiation in the latent space, we will get different color channels out. And all these color channels are compatible with the given grayscale image. So that means we get diverse solution for the colorization problem, and that's how it looks like. Yeah, so these are 9 different images that our conditional invertible network produced for the same grayscale image. And at this point, I usually ask the audience to guess which of these 9 images is the ground truth color image. Yeah, so you can label these row wise. So 1, 2, 3, first row, 4, 5, 6, second row, 7, 8, 9, third row, and just put your guess in the chat which one is the true color image. Okay, I get a few answers. So there are many different proposals, but as always, there is a very small majority for the correct solution. And the correct solution is number 8. Yeah, and it turns out that crowdsourcing better pure guessing. Yeah, I also saw a question by Param. I think I will answer that later when I will come back to that architecture. Yeah, please ask your question again. Okay, so here is a little bit more detail about the CINN architecture for that application. So here the coupling layers are now convolutional. So meaning that that the S and T networks are convolutional networks. And in addition, we use this wavelet flow trick that Markus described. So when we have a 2 by 2 pixel space, we recode them into 4 channels. So A is the low resolution pixel, and H, V, and D are the detail coefficients. Yeah, and then we split off the detail coefficients and keep processing only the lower resolution image and do this several times. And in the end, when the lower resolution image has very low resolution, we just add a few fully connected layers. That's how this architecture works. And the H, so the feature pre-processing network, is essentially a VTG. So here are some more results. So diverse colorizations. So, and the important thing to note here is that the colors do not tend to leak out of objects. Yeah, so if you do colorization naively, then often the colors will leak out across the borders of an object. Or what's also not good is that the color implausibly changes within the same object. So you see this a little bit here in the mushroom image. Yeah, so the color is more bluish on the left and more reddish on the right, which is kind of implausible. And the conditioning on the grayscale image, which includes edge detection, figures out where the color boundaries should be. So another question that we asked, so how does the latent space look like? And here we did some latent space interpolations. So in this case, we interpolated from a true latent representation, so which is here, the last but one image, towards the origin of the latent space and away from the origin of the latent space. And you see that the color saturation decreases as you go to the origin of the latent space. Yeah, and directly at the origin, so it's not exactly the same as the grayscale image, because apparently the network has learned that pictures of birds and vegetation tend to be brown greenish and not purely gray. So this is still more likely than a purely gray image. If you go the other way, away from the origin, then you get oversaturated images. Yeah, so you see that the latent space learns some emergent interesting structure. So we have no loss that enforces something like that. It just happens on its own. Here's another application. So we can do color transfer. So we take the grayscale information from the left car, so this one, and then we take each of the top cars, transform them to the latent space, conditioned of their actual grayscale information, but then replace the condition of the actual car with the new condition given by the car on the left. And then we invert the neural network, and we see that we get color transfer. So the condition determines the shape, the geometry, and the image where we took the latent color codes from determine the colors. Yeah, and you see some differences between the colors, and that comes because the grayscale image is quite dark here. So it is incompatible with light green, for example. So the network produces a darker green, which is compatible with the grayscale information. Same thing here for the red car. So again, 2 questions. Good question by Marcel. I can't answer that. I will ask the student who actually implemented the networks these questions. I think he never got to -z. Yeah, so can the latent representations transfer to other tasks, like how autoencoders can be used for representation transfer? Yeah, we are still trying to figure out how we get good structure in the latent space in order to actually do that. So there are some preliminary results, but it's still work in progress. So here's another application. So here we have day to night transformation. So on the left-hand side, the conditioning input, Y, is a daylight image, and the output are night images of the same scene. And on the right-hand side, we see the ground truth night image. But since we have a normalizing flow networks, we can always create diverse outputs. So, and if you look at these pictures, so all these night images look quite plausible. Not much less plausible than the ground truth night image. Yeah, and then if you look at what the conditioning network, so the pre-processing and feature detection network for Y learns, you see that it comes up with a multi-scale decomposition of the input that maybe that carries feature of different sizes that are relevant for the transition from day to night. So for example, in the coarsest level, you see mainly edges and blobs, so texture blobs, so that the network knows where object boundaries are, where the colors should not leak through. Then the second level detects mainly foreground versus background. Yeah, so because foreground objects need to be treated differently than background, and especially sky. And then the third seems to have a detector for populated areas, because these are the regions where you have to switch on lights in the night image. Yeah, so the network learns where it is plausible to switch on lights in the night image. So there are no lights in the mountain parts of the image, or in the sky, or in the forest. Yeah, so this is quite amazing, because we never had any loss enforcing this type of structure. It's just emergent structure in the latent space. So there are a few questions. What exactly is visualized in these feature images? So it's the strengths of certain channels in the feature pre-processing networks. Yeah, so you may know the feature the paper called feature visualization. Yeah, and it's a bit similar to that. So it shows pixels that have a very big influence on some pixel in the intermediate representation of the feature detection network. Yeah, and our interpretation that some things are edges and some things are populated areas were, of course, added in hindsight. Yeah, so green is positive and purple is negative, or I think in level 1 it's just 2 colors. So I think it's purple is positive for one type of feature and green is positive for another type of feature. So now, how would you compare and contrast normalizing flow-based models with score-based generative models? I don't yet have the answer. One student is working on comparing them in more detail. Yeah, so Markus would like to answer.
I'll just add a little bit to that. I mean, I think the diffusion models are really interesting. I kind of put them in a similar class to something like VAEs in the sense that they're generative. They're approximate models in certain ways, right? So like you don't get exact likelihood or exact density evaluation and things like that for the models. I mean, they're super exciting. I've been blown away by some of the results that I've seen recently. But I think flows, what I would argue is kind of a unique benefit of flows is this exactly tractable density function that basically none of the other generative models, modern generative models, including the diffusion models, has. And so depending on your application, that is a particularly attractive feature.
Okay, I don't see more questions, so I will go on. So one major application, as I said, is solving inverse problems with invertible neural networks. And here is a toy model that motivates the approach. So suppose there are hidden parameters x1 and x2, which for simplicity should be standard normal, that we would like to determine. But the only thing that we can observe is y, which is the sum of these two variables. Yeah, and I call this function g, that computes the sum of the hidden variables. And now in order to determine the x's from the y, we would need the inverse function of y, but of course this doesn't exist because the function g loses information and thus cannot be bijective. Yeah, and what people usually do in this situation is to add some regularization, which resolves the ambiguity of the inverse. For example, if we take the minimum norm solution, then what we will get is that the best choice is to set x1 equal to x2 and both equal to y over 2. Yeah, but this solution, while it is the maximum likelihood solution or the maximum a posteriori solution under some assumptions, totally disregards the ambiguity that there are infinitely many combinations of x1 and x2 that give rise to the same y. Yeah, and in many applications, that's not acceptable that you just disregard the ambiguity of the solution. The Bayesian solution to that problem is that we introduce a new latent variable z, which we define as the difference between x1 and x2. And now we can have an augmented forward process, g augmented, of x and y, which gives the sum of the two variables and the difference of the two variables, and which is now invertible. So we can, when we have a y and a z, we can just compute the x1 and x2 by the inverse function x plus z over 2 and y plus z over 2 and y minus z over 2. Now, of course, we do not know z. We only have introduced z conceptually, in theory, but we cannot observe z. If we could, then the problem would be solved. But what we know is the distribution of z. Because when the x1 and x2 are standard normal, so then z must be a Gaussian with twice the variance, so variance 2. And this gives us the opportunity to solve the inverse problem by sampling. So we have some actual observations, and then we take capital T samples. So we sample a z from the Gaussian distribution, and then compute the inverse with this particular z and the given y. Yeah, and this is well defined because this augmented function is invertible. And then we repeat this many times, and what we get is a sample of pairs x1 and x2 that are all compatible with the observation y, so that all sum to y, and at the same time follow the true Bayesian posterior of x1, x2 given y. And the reason is that we sampled z from the correct latent distribution, which in this case we could compute analytically. Yeah, and you can easily prove that if you sample the missing information from the right distribution, then you get samples from the correct posterior. Yeah, and now the idea is, how can we do this with INNs in more complicated cases? So where G is a complicated nonlinear formula, and we have high dimensional problems and so on. So, and here is an example what we achieved, and I will later explain how we did it. So in minimally invasive surgery, as in the picture on the right, so the surgeon does not really cut into the bodies, but only has these small devices. So one of them is a camera, and the others are tools that they use in order to do the surgery. Yeah, and here on the left-hand side is an example of what the surgeon might see in the camera image. And one important problem is that they would like to know the state of the tissue, for example, the blood oxygenation in some parts of the tissue, in the blood vessels especially, in order to know, for example, if they disrupted the blood flow correctly. So before you can cut into the tissue, you have to disrupt the blood flow by some clips. So for the layman, the clips are hard to see, but they are there. And then if the clips are placed correctly, the blood flow will be stopped, and then the surgeon can cut. And since you cannot see this in the normal camera image, what surgeons do is they cut very, very carefully a little bit. And if blood comes out, then the clip is not tight. So they need to set more clips, better clips. Yeah, but if you have a multispectral camera, then you can actually calculate the blood oxygenation. And then if it gets blue here in this false color image, then it means the blood oxygenation goes down, which means the clip is tight. Yeah, because oxygen cannot flow in. Yeah, and the task is now, given the spectrum, find the posterior distribution of the tissue state parameters. And you do this by a forward process that is some Monte Carlo simulation. So here's a sketch of the simulation. So on the left are the tissue parameters. And then there is some kind of ray tracing or particle-based model that simulates the light going into the tissue and coming out. And then you get a spectrum, a theoretical one. And then you discretize the spectrum according to the properties of the camera you would like to use. Yeah? And of course, there's a lot of information loss when you look at this spectrum. And the inference is the opposite. Given the spectrum, get the distribution of the tissue parameters. And we do this exactly as in the toy example. So we sample multiple times from the latent distribution Z, and then execute the inverse INN. And this gives us a sample from the posterior distribution Y, X given Y. Yeah, and many of these samples characterize the full distribution. So here are some outcomes for 5 tissue parameters: oxygenation, volume fraction, scattering, thickness, and isotropy, and 4 methods. So the second row is the invertible network. The first row is a classical Bayesian method by the name of approximate Bayesian computation. Immensely expensive, but if you can afford it, it gives exact results, or close to exact. And then 2 other neural networks: conditional variational autoencoder with inverse autoregressive flow, and dropout Bayesian inference. And you see some interesting properties. So first of all these methods more or less can determine the blood oxygenation quite accurately. So that's a good thing. But here you see that in a skewed distribution, the INN is able to recover a skewed posterior, whereas the others recover more or less symmetric posterior, which have a lot of mass in the impossible region. Yeah, there should not be mass beyond that line. By the way, the gray distributions in the background are the prior distributions for these parameters that have been used to control the simulations, and the colored one are the posteriors after observing the spectrum. So if these distributions are different, then the network has learned something by observing the data. Yeah, and here is a counterexample. So the thickness and the anisotropy parameter are unrecoverable because the posterior distribution looks essentially the same as the prior distribution. Yeah, it's not very well visible in ABC because we didn't have the resources to run it long enough to recover the correct distribution. So it's a very noisy version of the gray distribution. Yeah, and the other networks still have very peak distributions. Also, they should have a uniform distribution. So they pretend to have detected something here. And this is clearly overconfidence. So, and this is a very nice feature of these INNs, that you can also detect when the network knows nothing. Yeah, we know the unknown, so to speak. Yeah, and similar for the correlation. So the correlation of the INN is pretty much correct, whereas the autoencoder has positive correlation where there should be -1, and the dropout inference has no correlation at all. Yeah, so you see the advantages, and here is another application. Experimental design. So which spectral camera you should use. So a standard RGB camera would have 3 spectral channels. So this is a special RGB with very narrow sensitivity to the colors. And then there's a camera with 8 spectral channels and one with 27. And the one with 27 is hugely expensive. So you would rather not like to use that. So now you can train the neural network with all these different cameras and then look at the posteriors. And then you see here in the left posterior that there is a bimodal distribution. So it has 2 peaks, and the ground truth peak indicated by this dotted line is the smaller of the 2. So the highest peak is a little bit off, and that's nothing that you would like to see in your posteriors. Then the next posterior is just very wide, so you have a high uncertainty and the ground truth value is quite far off from the maximum likelihood value. And here in the third one, that's what you want, a nicely single peak, narrow distribution. And it turns out that the right distribution comes from the 8-channel camera and the left ones from the 3-channel camera. So, and the conclusion is that the camera with 8 channels is good enough. So the 27 is also good, but is not necessary. Okay, so are there questions? There's one question. No, only a thank you. Yeah, please just ask if you have questions. So now, just as a reminder, the architecture we used here in this application is what we call the split latent space. So latent space consists of the observations and the Z variables. And for the observations, we just assume Gaussian noise so that we train them with the squared error, with the squared loss. And the Z's we assume to be standard normal, as always in these models, and train with maximum likelihood. And then we also have a loss that ensures that y is statistically independent of z, so that the z's actually contain the information that's not in y and are not redundant with the information in y. Yeah, and that then we train in the forward direction using the simulated data, and then we run the network in the backward direction and using using the actual spectrum that we observed, and then we get out the tissue parameter and especially the blood oxygenation. Another question. When dequantizing your image data, are you applying the same distribution as your noise model? Not quite sure. I think dequantization here in this is not so critical. I think the resolution, the color resolution of the cameras is high enough. So there are no more questions. Oh, there's another question. Okay. So here again, the three architectures that I want to explain. So we are now here in the, we were now on the left-hand side with the last application. Now we go briefly to the right-hand side and to the conditional INN, where the y is fed into as a side input. And here is, and I will show this very briefly, a method that we call base flow, where we took this approach that I just showed one step further, using now a CINN and not a split latent space. And it's applicable whenever we have a good understanding of the forward process. So how the observations arise from the hidden parameters in terms of a simulation or a differential equation or whatever. Yeah, and then we can use this simulation to train the network and then only use the real data for the inverse problem. So running the network backwards. So you can imagine this as a pilot that learns flying only in a flight simulator, but the flight simulator is so realistic that after training, the pilot can go to a real plane and just fly the real plane without any additional problems. Yeah, and this is model-based inverse inference, and the traditional methods like regularization with the ambiguity and MCMC sampling methods are too expensive to be practical. And the INN can solve this. So that's what I already explained. So we train forward with synthetic data and use the backward process for the real data. And here is an example where we do this for the COVID-19 modeling. So we have 6 compartments. Probably anyone has seen such a simulation already. Yeah, so susceptible exposed carrier and so on. And then these are outcomes of simulations. So this is a website called the Epidemic Calculator, where you can do your own simulations. And this is all implemented using differential equations. And then this is how the network looks like. So here's the invertible part. So the latent noise and the posterior distribution that we would like to determine. And here the pre-processing part consists of 2 networks. So we take the time series of the observed cases, so the infected, the recovered, and the deceased people. About 80 days in total. And then we pre-process these with a convolutional neural network, which does feature detection and denoising of the data. Then an LSTM, which reduces the flexible size of the time series to a fixed size representation. And then this fixed size representation is the condition for the invertible part. And then we get out the posteriors that we want of disease parameters. And here are the marginal posteriors. So, and you see that the priors shown in the background are very different from the posteriors for most parameters. So we actually learned something from the data. Yeah, and these are 34 parameters. Some of them are from the differential equations, but then we have some additional ones in order to model the reporting errors, the reporting delay, and the unreported cases and things like that, and the reporting noise. And also an intervention model. So when the government put into effect some countermeasures. So that's why we have so many parameters. And the most interesting may be this one, the fraction of undetected infections. According to our model, we have a median of 63% undetected and a maximum likelihood, maximum of posterior resolution of close to 80%. So meaning that only 1/5 of the infected people back then in the first wave in Germany were actually diagnosed of the disease. And that's of course quite bad if 80% of the people run around without knowing to be ill and can infect other people, right? So you would never isolate the ones that are silently infected. Yeah, so here we have analyzed the uncertainty calibration, which means that when we have a confidence interval from our network with Q% confidence, then when we compare this to the actual data, then the network should be right Q% of the time. Yeah, that's what Q% confidence means. So, and you can do this for all kinds of different confidence intervals and compare the actual distribution, and then you should get a uniform distribution. And you see that the network actually has quite close to a uniform distribution. So the bands are the expected variance of the uniform distribution. So it is really neither overconfident nor underconfident. And this is a very nice property that we observe very frequently for the invertible neural networks. So here are the predictions of the time series. So to the dotted line is the training data, and then the extrapolation goes to with the estimated parameters. And you see that they are quite accurate. So for the German federal states. And the interesting thing is that you only need to train the network once. Yeah, and then you get an answer for 16 different states without retraining. That's a difference to MCMC, where you would have to run the algorithm from scratch for each state. So, and here are some other applications of this. We applied this to photoacoustic imaging, to particle physics, astrophysics, environmental physics, cognitive science, inverse kinematics, mechanical engineering, finance, and so on. So this finance application is especially interesting. So it's independent work. And it shows that the posteriors are not only faster than what we get from MCMC, but also more accurate. Yeah, so an identifiable parameter should be a diagonal in this diagram. And this is much closer to the diagonal than the MCMC results. So we are gaining confidence that the posteriors of our models are actually close to correct, because they work in so many different applications from independent people. Yeah, and they all consistently get quite accurate results. So is there a question? Yeah, there are 2 questions. Karam thinks that training using the latent split is only partly maximum likelihood based. Yeah, I would agree, and we hardly use this method nowadays. I just mentioned it because it was historically our first idea and because it worked so nicely in the surgery application. But nowadays we would, if we had to do the project again, we would use a CINN or a base flow. So then Danya asks, is it true that if CINNs underfits in model-based inverse problems, there's no guarantee that the inverse estimate would be correct? Yeah, so I think this is a very good question. So we are still in the process of investigating what the typical errors of invertible networks are. So for example, sometimes we see that the data distribution has heavier tails than the latent distribution. And then if you plot the latent distribution that are learned, then you have a central part that looks roughly like the desired Gaussian, but then you have more mass outside the central part in the latent space than a Gaussian should have. Yeah, and Markus has a very interesting paper about this type of problem, which he might want to comment on.
Sure. Yeah. I mean, tail behavior is kind of an interesting phenomena. Like, I think Ulrich's right. We're still in, let's say, the early stages of understanding what these various transformations are actually doing. You know, when we do something like a coupling flow versus a neural ODE based thing versus a res flow type thing, you know, what does that really mean in terms of distributions that we're fitting? And as Ulrich alluded to, I had a paper at ICML last year where we showed that if you care about tail behavior, the way that you construct a normalizing flow is actually really important. And you might end up getting a model whose tail behavior just reverts back to the tail behavior of whatever your selected base distribution was. And in fact, there was a related paper that came out, I want to say at AI Stats this year, which looking at a different problem, but was argued that some of those those properties of flow-based transformations that result in the tail behavior not being modeled well are actually necessary for stable training. And so in the ICML paper we had last year, we argued that, well, what you should really do there is tail behavior is kind of a very weird and very, very particular behavior of a distribution. And so if that's something that you care about, then what you should do is change the base distribution that you're using for the normalizing flow in order to better capture tail behavior, as opposed to trying to change the transformation itself.
Yeah, so in toy problems where we can analyze the errors in more detail, we see that the INNs tend to place mass in data space where there should be no mass. Yeah, so they place outlier samples. The opposite case, that there is no mass where there should be some, which would be the phenomenon of mode collapse, for example, does rarely occur or not at all. Yeah, so that's the general observations. But as Markus said, we are still in the process to understanding better what's going on with these flows.
I would also add, just to, and kind of a tangent from Moritz's question here is, there's a tendency to want to think about these transformations as the same way that we think about layers of a neural network. And in computer vision, we think about layers of a neural network as extracting feature representations of our data. And you can kind of do that if you want to, but I think it gives you the wrong intuition. Like, it's useful to do that if you want to try to visualize things and from that perspective, but in terms of what these layers are actually doing, I think thinking about it as feature representations is probably the wrong way to think about it. I think the ODE based representation is kind of a better understanding where you're kind of massaging and pushing probability, pushing mass around your space with these transformations. I think that kind of is a better intuition for what these models are doing. But again, it's still kind of, I don't know that anyone has the right, exactly right way to understand these just yet.
Yeah, but I will come to explainability issues in the remaining part of the talk. So Moritz asks, how do you account for problems with respect to the feature extractors? So, I mean, if the feature extractors are hard to understand, that doesn't matter at all, because it's not we that have to understand them, but the INN. Yeah, and it will take care of it by passing the appropriate gradients to the feature network. If it is not reliable, then of course the posterior will suffer. But since we start with networks that we know perform well, for example, on classification, then that's probably not that big of an issue that the networks, the feature detection networks, are too weak or so. Yeah. That said, so also another colleague is just now investigating what happens if the model is misspecified. So he trains with one model and then generates test data from a slightly different model and looks at how wrong the posteriors come out. And it seems that, so preliminary results suggest that the posteriors are now no longer the ground truth posteriors, because the network does not know how the ground, so the test system behaves, but the posteriors are the best possible given the original model. Yeah, so he came up with some toy models where you could actually compute the best possible approximation of the test model given the training model. And that seems to be the result, what the INN returns. And this is also kind of reassuring, because it is sort of graceful degradation. Yeah, you can never expect to perform better if you are outside the function class that you have trained on. Okay, so now let's come to the disentanglement part, and then final one is the IB-INN. So here again, the three types of architectures. Now we turn to the middle one, with the latent space being a Gaussian mixture model. Yeah, and to emphasize the difference again, so in the CINN, we model the conditional distribution by sampling from a standard normal and then transforming it to the data space by a function that depends on Z and Y. And in the latent mixture INN, we sample from a Gaussian mixture model in the latent space that depends on Y, is conditioned on Y. And then we just transform the Z's to X. So, but in both cases, we get a conditional distribution of X given Y. Yeah, and it turns out that this is especially useful for disentanglement. So what is disentanglement? Disentanglement means that the latent features should have a interpretable effect. So each feature should have a single interpretable effect. And here's again an example from the GLOW network that Markus talked about. So here we have latent features like smiling, age, narrow eyes, blonde hair, and beard. And then you have these sliders, and can try this with your own face on the website given. Yeah, and then if you turn up smiling, then you will smile more. Or if you turn down age, you will look younger. Yeah, and the point is that each variable is a single concept, but the effect in the data space is a very, very coordinated change of many different pixels. Yeah, a single variable in Z influences many pixels in X in a coordinated way. And that's the point of disentanglement. So here's the definition by Benjo, so which I will skip. So here's some prior work. So the standard VAE is not able to disentangle, for example, between to disentangle the pose variable, so where the person looks like or how the head is oriented. Yeah, so when you change the pose, then the appearance will also change of the person. So for example, it will get eyeglasses or will turn from a woman into a man. Yeah, that would be entanglement. And a beta VAE partly solves this. So here the disentanglement is much better, and they achieve this by adding a particular loss term to the latent space. Yeah, so here are is another result. The what's the ID gun, but I will also not go into details here. Now a word about two different types of disentanglement. I already talked about this earlier. So the fundamental disentanglement disentangles the latent space into the content and the noise. Yeah, so some variables are content and the others we can safely ignore. And then among the content variables, we can do more disentanglement in order to disentangle the different concepts of the content, like age and smiling. Yeah. So, and these are actually two separate problems. To first, factor out the noise and then to disentangle the content into sub-features. So here is a classical algorithm, linear PCA, which is trying to do the fundamental disentanglement. So you do the eigendecomposition and then sort the eigenvectors according to the magnitude of the eigenvalues. Yeah, and then you get a spectrum that typically looks like this. But here, so it, of course, because you sorted it, the importance goes down, but there is no clear point where you should cut. Yeah, so where does the important dimensions end and where do the noise dimensions begin? That's not clear in PCA most of the time. In contrast, in this nonlinear ICA that I'm going to show, the spectrum looks like this. So we have a very pronounced knee, which suggests a clear cutting point. So this is MNIST or eMNIST, extended MNIST, where the knee says that the first 22 variables are the content and the remaining ones are the noise. Yeah, and here's what happens. So this would be PCA. Yeah, it would try to approximate the main directions of the data by Gaussian. And it only works kind of if the data is not actually Gaussian. Yeah, so it is unable to disentangle non-Gaussian data. So this is independent component analysis, a bit better, so that the directions that it finds don't have to be orthogonal in contrast to PCA. Yeah, so, and then you get independent dimensions in latent space, which are here not Gaussian, yeah, but they are still independent. And then nonlinear ICA can find curves in the data space and turns them into straight lines in the latent space. And these straight lines are orthogonal to each other, so independent. Yeah, but the problem is that if you do independent component, nonlinear independent component analysis with an arbitrary nonlinear function, then there are too many possible solutions. So nonlinear functions are just too flexible, so they can fit anything in infinitely many ways. Yeah, here are two examples for the same data distribution and totally different. So if you map the latent dimensions to the data space, you get totally different shapes in the latent space. Yeah, And it turns out that it's impossible to resolve this ambiguity without additional information. So that's a theorem that has been proven by Hyvverin, the main guy from ICA. Yeah, and I will show this later. So here are two, here is a solution. So if we have additional information, in this case, a class label that allows us to structure the latent space as a mixture model. Yeah, now we have two mixture components, a blue and an orange one. And then by looking at how the colors are distributed in the data space, we can distinguish the different solutions. Yeah. So here, so this spiral thing would be very, very implausible if we would see this color distribution in the data space. Yeah, and that allows us to pick the right nonlinear function from the set of possible ones. So here's this important negative result. So if it's fully unsupervised nonlinear disentanglement is impossible. So that has been mathematically proven. But recently there were a number of positive results that if you have additional information, for example, temporal relations between the variables or multimodal observations, so from different measuring devices, different types of cameras or LiDAR and radar and camera, or class labels as on the previous slide, then you can resolve the ambiguity. And the interesting thing is that the latent mixture INN fulfills the requirements of this theory, so we can apply it. So I will skip this one, and I will also skip this one. So here are results for MNIST. So the disentanglement of this particular pair of nines would be that the angle dimension changed and the pen width dimension changed. Yeah, and here is what the network found. So the first 8 variables are global variables. So here are 4 of them. So the slant variable that everyone else also found, and the height variable that is a bit more rare in other work. And then comes something interesting. The width variable is in all other work that we are aware of a single variable. But we found that it's actually 2 different variables, one that controls the width of the top and one that controls the width of the bottom. Yeah, so you see this especially at the 8. So making the upper ring bigger has no influence on the lower ring. Yeah, and that's something that the network found out on its own without any guidance by us, except for the class label and the network architecture. So there's no loss that enforces something like that. And that's what we think is guaranteed by this theorem that we proved about the disentanglement. And apparently MNIST happens to fulfill the assumptions of the theorem. Of course, that's very hard to prove. But since it works so well, there must be something. So here are some of the local variables that have only influence to a very few letters and to very small parts of the letters. And the last one is my favorite. So it just wags the tail of the 2. Yeah? Yeah, and then if you go beyond these variables and change them in latent space, you see no visible effect. So these are the noise variables that you can safely set to 0 and ignore. And only the first 22 need to be transmitted. Yeah, so now for the last part, that's actually a paper that's also in the main conference. So it was at Europe's and then follow-up papers in the main conference. So you can talk to the original authors, which is using the latent space, the latent mixture INN for generative classification. So a generative classifier, as I already explained, uses Bayes' rule to compute the posterior of labels given the image, and does this by means of modeling the likelihood of the image given the label. And Why are we interested in these? We hope that they are more reliable and more interpretable. So we hope to get uncertainty quantification, outlier detection, robustness against distribution shift, against adversarial examples, and so on. And we also hope that the network will be able to discover meaningful feature like the one in the previous part. But DCs have been around for a long time, but no one is using them because their predictive power is just too bad. So their classification accuracy is just crap in contrast to the discriminative classifiers. So, and the information bottleneck principle promises to solve this. And what the information bottleneck principle is doing, it introduces latent variables Z, and then first the image X is transformed into latent space Z, and then the classification is only done on the basis of the latent features. And then this information bottleneck loss says that, so it is to be minimized. It says that the mutual information between X and the latent space is to be minimized so that only the essential information in X survives in Z. And the mutual information between the labels and Z should be maximized so that the classification accuracy is maximized. Yeah, and beta is a trade-off parameter between the discriminative performance and the generative performance. So here's the formula for the mutual information. And now what we do is we use here this architecture. This is the latent space that I just mentioned. And we use a Gaussian mixture model in latent space, because then the mutual information between the labels and the latent variables can be calculated analytically. That's very easy. Yeah, and the transformation between X and the latent variables is an INN. In this case, a latent mixture INN, because the latent distribution is a mixture distribution. The problem here is that the INNs are lossless encoders. So there is no bottleneck in Z, no information bottleneck. And in practice, this means that this mutual information between X and Z is infinite. So it diverges. So we cannot train on a number that is infinite. And what we found is that this can easily be solved by using noise augmentation. So if we add some noise to X, then the mutual information, so that the encoding will no longer be perfect. Yeah, so that we get the encoding of the noisy image and compare it to the original image, noiseless, and then this mutual information is actually a finite number that we can nicely train from. Yeah, and it turns out that the noise that we add here is the noise that we anyway add for dequantization. So we don't need to add more noise than we do anyway. Yeah, and then by doing some calculations that are in this paper, it turns out that the loss for the INN is essentially still the same. So we need to minimize the negative log likelihood of the Z distribution, so the latent mixture distribution, and we need to minimize the log of the Jacobian determinant. Yeah, just as before, only that we add some noise to the X, to the images. Yeah, and here is what comes out of it. So we trained it on CIFAR in the first paper and on ImageNet in the second one. So this is the one that is presented here in the main conference. And it turns out that it works quite well. So, and you can nicely see this trade-off between the generative capabilities and the discriminative capabilities. So if we have a small beta, the generative capabilities are emphasized. So we get a bits per dimension of 4.3 in comparison to a dedicated generative network, which has bits per dimension of 2.6. but this network is not able to do classification. So the classification performance on the latent space of that network would be terrible. Yeah, and in contrast, if you do use a bigger beta, then the classification accuracy is emphasized. And here for beta equal to 8, the classification accuracy is very close to a ResNet of about the same size as our invertible network. Yeah, so that's top 1 error, top 1 accuracy. So here's a illustration of the latent space of the CVPR example as we increase beta, so 2-dimensional projection. So this is for a very small beta. So it looks more or less like a Gaussian distribution, but the classes are very mixed up. Yeah, and then if we increase beta, the clusters separate more and more from each other. And it means that the classification accuracy goes up, but the generative capabilities or the image quality when we sample goes down. Yeah. Now for the interpretability part, so what do we gain? So here, heat maps are an intrinsic property of this architecture. So we don't need heat maps in retrospect. We can just generate them from the latent space. So where are the high magnitude values in the latent space, and then we just backpropagate the high magnitude values. And then here, the high magnitude values for the bow tie class are the yellow ones. Then the high magnitude for the suit class and the high magnitude values for the sun classes. So you see that the heat map actually emphasizes the region containing the corresponding class. Yeah, or here for the dog. So looking at the dog's face, it thinks it's a Rottweiler, which is the true label. But it could also be an Appenzeller, so I have no idea what the difference is. But it also sees a soccer ball. Yeah, and that's true. Also, soccer ball did never appear as a label in this particular image. So it says always only one label per image. Yeah, so this gives you a lot of confidence that the network is doing a sensible thing when it takes its decision. So here's another thing. So we can look at the distances in latent space between the mixture components for different classes. And what we find is that the different types of cats, so tiger, Egyptian cat, tiger cat, and tabby, are quite close to each other in the latent space. And also different kinds of foxes are close to each other in the latent space, whereas the different types of animals are quite far away in latent space. So here the outlier is the Arctic fox because it's white and not brown. Yeah. So here is another illustration of the same thing. So here a highly confident decision for a Grönendal dog. So there the latent representation is very close to the cluster center of the Grönendal class, to the mixture component. So here is an ambiguous decision. So it could be a missile or a projectile. And so the latent representation has the same distance from both class centers and is within the region of both, within the trust region of both. Here is a case for multiple objects. Here so it is a refrigerator, which happens to be the true label, but you also see a cat, which is a class that appears but is not in the label. And then the latent representation is in between the two classes. Yeah, and here is a wrong classification. So it should be a sheep, but the closest classes are camel and seatbelt. No idea why seatbelt is close, but it's outside the confidence region, the latent representation. So it knows that it does not know. Yeah, and this is illustrated further here. So here, when we have two classes in the same image, then both classes should get a high value. Whereas if we have none of these classes, we should get a low value for both classes. Yeah, and then we can have a threshold that distinguishes ambiguity from out of distribution. Yeah, and that's something only a generative classifier can do, because in a discriminative classifier, the probabilities must add up to 1. So these would be scaled up to unrealistically high confidence values. Yeah, and that's also one reason why discriminative models are so prone to adversarial attacks. Yeah, and here is a artificial experiment. So we did artificial distortions like color distortions and noise distortions and adversarial examples. And you see here that the threshold can distinguish inliers from outliers at 97% accuracy. Yeah, so in practice, all this is not yet as perfect as it might appear here in the talk, but we are making good progress to making these networks better and more interpretable. So the last thing I would like to show again is the uncertainty calibration. So the thing with the 90% confident interval should be correct, should be hit 90% of the time. And here is it for a ResNet, where it is pretty terrible. Whereas for the IB-INN, it is close to perfect. Yeah. So you can much more rely on the uncertainty quantification of an invertible network in comparison to a classical network. So that brings me to the summary. So our networks can all be found in this public library, Freya. So the basic code for the networks and the specific code for the various papers that we built upon that. And INNs are quite good density estimators, not quite as good as GANs, but we started later and don't have as much compute as the big guys. And the good thing is that INNs have much stronger mathematical guarantees and interpretations than the GANs at the moment. And that is also our focus in the research. I showed you 3 types to model conditional distribution: the conditional INN, the latent mixture INN, and the split latent space INN. And in all these cases, we get full posteriors. I should have mentioned this: classical approaches often give you only the marginal posteriors, whereas the INNs give you the full joint posterior. So you can also see the correlations between the variables that many classical approaches ignore. So the correlations are missing from the uncertainty estimates, but not so in the INNs. Some future work is, of course, to improve everything and to strengthen the guarantees that we get. So hopefully we will be able to actually mathematically prove that something will happen, such as disentanglement under certain conditions, or that we can prove convergence rates or so for towards the true posterior. That would be very good. And then we work on lots of applications, as I indicated. And one especially interesting thing is how we could incorporate prior knowledge from various fields. So for example, the physicists have 200 years of equations and they don't want to throw it away and just start from scratch using data. So they want to combine data with what they already know. And that's a very interesting problem. And with that, I would like to thank all my collaborators. And I would like to show you the references, but we will upload them later so that you don't have to remember them now. So that's what I wanted to show. Thank you for your attention.
Thanks, Ulrich. Yeah, so if there's any questions for Ulrich, I know we're about 10 minutes past our nominally scheduled time. Hopefully no one minds too much. If there's any questions for Ulrich, yeah, great. Peter has a question here. So sampling, I think this is for you, Ulrich, but.
Yeah, so that's a very interesting question. So many classical uncertainty quantification methods just assume that the uncertainty would have a Gaussian distribution. And interestingly, this assumption is often true, but in many cases you are not sure. Yeah, so it kind of works, but you aren't sure. And then you can train an INN and then analyze the posteriors that the INN gives you. And then according to how these posteriors look like, you can decide which of the simpler models would be appropriate for that particular application. Yeah, so if you see that the INN always produces Gaussian posteriors, there is no point in taking all the burden of an INN. You can just use a heteroscedastic model that gives you the mean and the standard deviation directly. And similarly for other types of cheaper parameterized distributions. So, and of course, you can then either train these parameterized models using the INN as a teacher, or you can train them directly from data, just using the INN as a verification that you are on the right track.
Great.
So are there more questions?
Not seeing anything else in the chat here. Oh, it looks like
Moritz asks. Sudeepa asks, how can I interpret the relation or difference between normalizing flows and INNs? Yeah, so I'm not sure whether this is official, but in our research group, we just say that INNs are more or less the coupling layer architecture. So the ones that are efficient in forward and backward direction, and the ones that have cheap Jacobians. Whereas the normalizing flows are more general, so they contain all the mathematical possibilities to build invertible models with these properties regardless of efficiency.
Yeah. It's a good question of terminology, and we probably should have done a better job, Ulrich, of having a good coordinated answer for that. I mean, I think I view it somewhat similarly. I also think that there are, normalizing flows for me carries with it the specific concept of the generative model, whereas there are lots of interesting applications of invertible networks where maybe we don't care quite as much about the generative model component of it, but we just care about the fact that the function itself that we're learning is invertible and therefore, for instance, preserves information. And so I view INNs as actually maybe a little bit of they're kind of, if you draw a Venn diagram, they're strongly overlapping, but they both have some kind of independent components, right?
Mm-hmm. Yeah, also the name of normalizing flow is not always really true.
Yes.
If the latent distribution is not standard normal, then we actually would have a GMM flow or so, but the name is still applied to them.
Yeah.
So then Moritz, what kind of images does the INN produce on ImageNet? So I would like you to ask this question to my colleagues that present that paper on the main conference. So Radek Mackowiak and Lyndon Artisoni will be present on the main conference. So I will warn them to prepare some nice examples.
Okay. So unless there are any other last questions here, perhaps I'd like to just say thank you to everybody that attended. I know many people have already dropped off, but thank you to them as well, even if they're not here to hear it. It was great to have such a large crowd and lots of questions throughout and at the end that made this a lot more fun than ECCV. I don't know how you felt, Ulrich, but I feel like that was, it was much more fun for us than just pre-recording something and putting it up. So if you have any other questions or comments or feedback or whatever that you'd like to give, feel free to find us online. Our emails and everything else is easily Googleable. And we will. This is being recording, and we'll be posting the recording and the slides and links and everything to the website to the tutorial website, probably sometime in the next week or so. So keep an eye out for that. And yeah, any last words from you, Ulrich, before we wrap?
Yeah, I would also just say thank you for the great questions. And yeah, I see this also in lecturing at the university. So doing an online course is much better than just uploading the videos or the script. So much more fun, and also for the students. So it's great that CVPR gave us this opportunity to actually present it in person. Yeah, and then I hope, I hope to get a lot of feedback from you, or requests or ideas for interesting follow-up work.
Yeah.
And users of the Freya library.
Yes. Okay. Well, I'm gonna stop the recording now. So thanks everybody, and hope to hear from you again sometime soon, and maybe actually run into you in real life at a conference at some future CVPR or ECCV or whatever. So